Imagine witnessing a cosmic event so grand that it reshapes our understanding of existence. A star exploding with the brilliance of a billion suns, galaxies colliding in a dance of gravitational forces, or the birth of a black hole that warps the very fabric of space and time. These spectacles unfold on scales so vast that they transcend the brief flicker of human experience. We are, in cosmic terms, merely visitors passing through a snapshot of the universe's eternal timeline, our entire civilization's history occupying less than a cosmic blink. 8 billion years before us, and will continue for countless trillions of years after the last human is gone. This sobering realization places us in a unique position, aware of our cosmic insignificance, yet blessed with the capacity to comprehend the grand narrative unfolding around us. Time, in the cosmos, flows differently than in our daily lives. While we measure our existence in decades, cosmic events unfold over millions, billions, and even trillions of years. A single orbit of our galaxy takes 230 million years, a period so immense that when dinosaurs roamed the Earth, our solar system was on the opposite side of the Milky Way, 5 million years ago, when our human ancestors were just beginning to fashion stone tools in the African savanna. The light from distant quasars has traveled for billions of years across the expanding cosmos, carrying information from an epoch when the universe was young and wildly different from what we see today. These vast temporal scales affect every aspect of cosmic evolution. Stars like our Sun live for around 10 billion years, while the smallest red dwarfs may shine dimly for upwards of 10 trillion years. Galaxies evolve over hundreds of billions of years, their spiral arms unwinding and rewinding, their central black holes growing with each consumed star. Even the atoms that make up our bodies and our world undergo transformations over cosmic time. Elements created in stellar furnaces, scattered through space in supernova explosions, and eventually incorporated into new star systems and planets. This disparity between human timescales and cosmic ones creates a poignant reality. Some of the universe's most magnificent events will never be witnessed by human eyes. The universe moves with patient indifference to our presence. Stars form, live, and die over billions of years. Galaxies collide over hundreds of millions of years. And the universe itself evolves over time spans so vast they challenge our comprehension. Our species has existed for a mere 200,000 years, less than a heartbeat in cosmic time. 8 billion year history as a single Earth year, humans would appear only in the final minutes of December 31st. The written history of civilization would occupy just the last second of this cosmic calendar. Consider that the universe has already experienced more than 60,000 times the duration of human existence and will likely continue for at least 1 trillion times longer than we have already existed. The deep future holds cosmic events of such grandeur and scale that they make our current astronomical observations seem mundane by comparison. The collision of galaxies, the death of the last stars, the evaporation of black holes, these processes will unfold over timescales millions and billions of times longer than our entire evolutionary history. Even if humanity survives for millions of years to come, evolving into forms we might not recognize today, we will still miss the grandest cosmic events that lie in the distant future. We are, in essence, cosmic mayflies, experiencing just the briefest moment of the universe's long evolution. Why does the universe operate on such incomprehensible timescales? The answer lies in the fundamental forces of nature and the immense scales of cosmic structures. Gravity, though the weakest of the 4 fundamental forces, shapes the largest structures in the universe. Its influence accumulates gradually over vast distances, slowly but inexorably pulling galaxies together or pushing them apart. The nuclear forces that power stars operate in a delicate balance, allowing them to burn for billions of years before exhausting their fuel. The sheer size of the cosmos also contributes to its languid pace. Galaxies span tens of thousands of light years across, with their constituent stars separated by trillions of kilometers. Even at the incredible speed of light, 300,000 kilometers per second, it takes time for causality to propagate across these distances. The Milky Way's diameter is so vast that light takes 100,000 years to cross from one edge to the other. This means that different regions of our galaxy are, in a very real sense, living in different epochs of time. The density of matter in the universe is another factor governing cosmic timescales. While stars and planets seem substantial to us, the universe is overwhelmingly empty. The average density of the observable universe is estimated to be just 5 hydrogen atoms per cubic meter, a vacuum more perfect than anything we can create in laboratories. In this diffuse environment, interactions between cosmic structures occur with extreme rarity, stretched across billions of years. The emptiness of space creates natural time dilation, where processes that might occur quickly in denser environments take eons in the cosmic void. Even the basic building blocks of the cosmos contribute to its measured pace. Stars like our Sun fuse hydrogen into helium at rates determined by nuclear physics, converting just 600 million tons of hydrogen to helium each second. While this sounds enormous by human standards, it represents only a tiny fraction of the Sun's total mass, allowing it to shine steadily for billions of years. These processes cannot be rushed. They are governed by the immutable laws of physics that set the universe's pace. Our understanding of these distant futures comes from the remarkable power of science to predict what we cannot directly observe. By studying the physics of stars, the motion of galaxies, and the expansion of the universe, scientists have constructed a timeline of cosmic evolution stretching far beyond human existence. These predictions aren't mere speculation. They're grounded in observations, experiments, and mathematical models that have successfully explained the universe's past and present. The cosmic predictions we make today represent one of humanity's greatest intellectual achievements. We have discovered fundamental constants of nature: the gravitational constant, the speed of light, the strength of nuclear forces, that govern how matter and energy behave throughout time and space. These constants allow us to simulate the life cycles of stars we'll never see born or die, to calculate the trajectories of galaxies over billions of years, and to project the expansion of the universe into the unimaginably distant future. Modern astrophysics combines observational data from powerful telescopes with sophisticated computer models that can simulate cosmic evolution. The same equations that explain the cosmic microwave background, the afterglow of the Big Bang, also allow us to predict the ultimate fate of stars and galaxies. By measuring the current positions and velocities of cosmic objects, scientists can rewind or fast-forward their motions with remarkable precision. 5 billion years, a prediction based on current measurements of Andromeda's motion toward us at 110 kilometers per second. Perhaps most impressively, scientists can now simulate entire virtual universes, starting from the conditions just after the Big Bang and watching as virtual galaxies form, evolve, and eventually fade away. These simulations, running on the world's most powerful supercomputers, serve as cosmic time machines, allowing us to witness in compressed time the grand events that will unfold over trillions of years. Through these tools, we can glimpse events we'll never live to see. This temporal limitation creates a unique melancholy, knowing that the universe's most spectacular moments will unfold in our absence. There is something poignant about realizing that the cosmic story will continue long after humanity has exited the stage. The stars will still burn, galaxies will still collide, and the universe will continue its inexorable evolution, indifferent to whether conscious beings remain to appreciate its grandeur. This realization connects us to the ancient Greek concept of cosmic tragedy, events of sublime significance unfolding according to their own logic, regardless of human desires or interventions. Yet there's also a profound beauty in this knowledge, a transcendent quality that speaks to something deeply human. By understanding what will happen billions and trillions of years from now, we transcend our biological limitations. Though our bodies are confined to a brief window of cosmic time, our minds can voyage into the distant future. This cognitive time travel represents one of the most remarkable features of human consciousness, our ability to mentally project ourselves across timescales that dwarf our physical existence. This capacity for temporal imagination sets us apart from all other known life forms. A lion may stalk its prey with cunning, a dolphin may recognize itself in a mirror, but only humans contemplate the heat death of the universe trillion of years hence. This ability creates a kind of immortality of thought. Though we are physically ephemeral, our understanding reaches toward eternity. The cosmologist who calculates the final fate of the last black hole is, in a meaningful sense, present at that unimaginably distant moment through the power of mathematical prediction. Consider the ultimate fate of our own galaxy. Right now, as you hear these words, the Andromeda Galaxy, a spiral of stars larger than our own Milky Way, is hurtling toward us at 110 kilometers per second, 5 billion years. Every second that passes brings these two galactic giants approximately 110 kilometers closer to their inevitable encounter. The merger will unfold in slow motion by cosmic standards, taking hundreds of millions of years to complete once it begins. The first approach will stretch the spiral arms of both galaxies into long tidal tails, as their mutual gravitational attraction distorts their elegant structures. Stars that have shone steadily for billions of years will be dislodged from their orbital paths, sent on new trajectories through the merging galaxies. The supermassive black holes at the centers of both galaxies, objects with masses millions of times that of our Sun, will begin their own gravitational dance, eventually merging in a cataclysmic event that releases gravitational waves rippling through the fabric of space-time itself. Despite the violent nature of this collision, individual stars within each galaxy are so widely spaced that direct stellar collisions will be extremely rare. Our solar system, if it still exists, may be flung into a new region of the combined galaxy, or may remain relatively undisturbed. But the night sky from any surviving planet would be transformed beyond recognition. Instead of the familiar band of the Milky Way, observers would see a chaotic swirl of stars in all directions, punctuated by brilliant regions where new stars are being born from compressed gas clouds. None of us will be present to witness this galactic merger, yet through science, we can envision the night sky it will create, filled with new stars born from the chaos of colliding gas clouds, the spiral arms of both galaxies distorted beyond recognition. Computer simulations show us frame by frame how this cosmic collision will unfold, allowing us to witness in compressed time an event that will take longer than the entire history of life on Earth to complete. Or imagine the death of our Sun, still billions of years in our future. When it exhausts its hydrogen fuel, it will swell to hundreds of times its current size, engulfing the inner planets and potentially even Earth itself. This transformation will create a spectacular red giant star that would dominate our sky, if anyone remained to see it. The aftermath will be equally dramatic, as our star sheds its outer layers in a beautiful planetary nebula before settling into its final form as a white dwarf. This stellar metamorphosis represents just one of countless transformations that stars undergo throughout the cosmos. Across the universe, stars 100 times more massive than our Sun explode as supernovae, briefly outshining entire galaxies before collapsing into neutron stars or black holes. Others, more modest in size, quietly fade into darkness over trillions of years. Each of these stellar life cycles plays out according to the immutable laws of physics, on timescales so vast that most will never be witnessed by conscious observers. These events represent the universe's grandest performances, played to an empty theater. No human eyes will witness the moment when the last star flickers out, when the final black hole evaporates through Hawking radiation, or when the expanding universe reaches its ultimate fate. Yet through our scientific understanding, we can know these futures and contemplate their significance. In this exploration of cosmic futures, we confront the limits of our existence while celebrating the boundless reach of human curiosity. We may be fleeting observers in the cosmic drama, but we have achieved something remarkable: the ability to perceive events far beyond our temporal horizon. Through this scientific foresight, we gain a perspective that transcends our brief lives and connects us to the universe's grand narrative. The knowledge of these future events offers a unique vantage point on our present moment. Against the backdrop of cosmic timescales, our daily concerns shrink to insignificance, yet our capacity to understand becomes all the more precious. We exist in a privileged moment, a time when intelligent life has evolved to comprehend both its past and its future, even as it recognizes its temporary nature. As we embark on this journey through the universe's future, we'll explore events of increasing scale and distance, from the relatively near collision of galaxies to the ultimate fate of reality itself. We'll contemplate what these events mean for the concept of legacy, for the potential of life in the cosmos, and for our understanding of time and existence. Though we'll never witness these cosmic spectacles directly, through science and imagination, we can experience a version of them, a testament to humanity's unique ability to transcend its limitations. The universe's future holds mysteries that challenge our comprehension, black holes that will eventually evaporate through quantum processes over timescales of 10 to the power of 100 years, the potential formation of exotic objects like Boltzmann brains in the distant heat death of the cosmos, and the possibility that the universe itself might eventually collapse back into a singularity, potentially giving birth to an entirely new reality. These concepts push at the boundaries of physics and philosophy alike, reminding us that our understanding, while remarkable, remains incomplete. Perhaps most profound is the realization that intelligent life, whether human or otherwise, exists in a remarkably narrow window of cosmic time. The early universe was too hot and chaotic for complex structures to form, while the distant future universe will be too cold and diffuse for the complex chemistry of life to function. We exist in what some astronomers call the stelliferous era, when stars shine brightly and provide the energy necessary for life to evolve and thrive. This privileged position allows us to study both the universe's past through the light of distant galaxies and its future through the predictive power of science. Our first destination on this journey through cosmic time takes us to an event already in motion, visible through our telescopes, yet unfolding too slowly for human perception. 5 million light-years from Earth, the massive spiral of Andromeda approaches our galaxy, setting the stage for a collision of cosmic proportions. Through our most powerful telescopes, we can see Andromeda's magnificent spiral structure, a disk of stars spanning more than 220,000 light-years, containing approximately 1 trillion stars. This galactic giant dwarfs our own Milky Way, which contains a mere 400 billion stars across its 100,000 light-year diameter. The approaching collision is not a matter of speculation, it is a certainty written in the motion of these galactic titans. Precise measurements using the Hubble Space Telescope have tracked Andromeda's movement relative to our galaxy, confirming that the two are on a direct collision course. 5 million kilometers closer to us, a distance that seems vast by human standards but represents just a tiny fraction of the gap still separating our galaxies. The scientific field of galactic dynamics allows astronomers to project this motion forward in time, creating detailed predictions of how the collision will unfold. The initial approach will begin with a near miss as the two galaxies swing past each other, their mutual gravity stretching each into elongated shapes. They will then curve back toward each other for a second, more direct encounter. With each pass, their stars and gas clouds will become more thoroughly mixed, until eventually, after perhaps 5 or 6 encounters over hundreds of millions of years, a single elliptical galaxy will form from their combined masses. While this event lies billions of years in our future, the gravitational dance has already begun, and the outcome is inevitable. Let us turn our attention to this approaching merger and the birth of what astronomers have already named Milkomeda, a new galaxy arising from the union of our cosmic home with its largest neighbor. By examining this future event in detail, we can begin to appreciate the grand cosmic processes that will continue long after humanity has vanished from the universe. In the vast darkness of intergalactic space, two colossal star systems are locked in a gravitational embrace, the Milky Way and Andromeda galaxies. This cosmic dance will culminate in one of the most spectacular events in our local universe, a galactic collision of unimaginable scale. Though appearing peacefully stationary in our night sky, Andromeda is racing toward us at more than 400,000 kilometers per hour, fast enough to travel from Earth to the Moon in less than an hour. 5 million light-years, this breakneck speed translates to imperceptible motion from our perspective. Only through precise astronomical measurements do we know that these two galactic titans are on a collision course. Andromeda, also known to astronomers as Messier 31, is the largest galaxy in our local group, a collection of more than 50 galaxies bound together by gravity. With a diameter of approximately 220,000 light-years and containing up to 1 trillion stars, Andromeda dwarfs our Milky Way, which spans about 100,000 light-years and contains between 200 to 400 billion stars. Both galaxies are spirals, with elegant arms wrapping around central bulges containing billions of older stars. At the heart of each galaxy lurks a supermassive black hole, objects with masses millions of times greater than our Sun, yet concentrated in regions smaller than our solar system. The discovery that Andromeda is approaching rather than receding from us came as a surprise to astronomers in the early 20th century. In an expanding universe, most distant galaxies are moving away from us, their light stretched to longer, redder wavelengths by the Doppler effect. But Andromeda's light shows a blue shift, a compression of its wavelengths indicating motion toward us. This revelation transformed our understanding of galactic dynamics, proving that local gravitational attractions can overcome the universe's overall expansion. In 2012, astronomers using the Hubble Space Telescope made precise measurements of Andromeda's sideways motion across the sky, confirming that the galaxies are on a direct collision course. The data showed that Andromeda isn't just moving toward us, it's aimed almost precisely at the Milky Way, with only a slight offset that will cause the galaxies to sideswipe each other in their first encounter before ultimately merging. These measurements allowed scientists to simulate the coming collision with unprecedented accuracy, providing a timeline for the cosmic merger that awaits our galaxy. 5 billion years from now, coincidentally, around the same time our Sun will be entering the final stages of its life. The first signs of the approaching collision will be subtle alterations to our night sky, as Andromeda grows from a faint smudge visible only on dark nights to a large, distinct oval clearly visible even under moderately light-polluted skies. As the galaxies approach their first close pass, Andromeda will loom larger than the full moon, its spiral structure clearly visible to the naked eye. This initial encounter will dramatically transform both galaxies. The immense gravitational forces at play will distort their elegant spiral structures, drawing out long tails of stars and gas in a phenomenon astronomers call tidal stripping. These gravitational tides will dislodge billions of stars from their original orbits, sending them on new trajectories through the merging galaxies. Some stars will be flung into intergalactic space, destined to wander the void between galaxies for eternity. Others will be pulled toward the centers of the galaxies, where they may eventually be consumed by the supermassive black holes residing there. Despite the violent nature of this galactic collision, the vast distances between individual stars make direct stellar collisions extremely rare. 5 light-years of empty space between it and the nearest star, Proxima Centauri. Similar vast gulfs separate most stars in both galaxies. This immense emptiness means that during the merger, stars will primarily be affected by the overall gravitational fields of the galaxies, rather than by close encounters with other stars. It's as if 2 swarms of bees pass through each other, with the individual bees rarely colliding due to the vast spaces between them. However, the same cannot be said for the gas and dust that fill the interstellar medium. These diffuse clouds of matter will collide and compress, triggering a spectacular burst of new star formation. Where these clouds meet, the increased density will cause portions of them to collapse under their own gravity, forming new stars at a rate hundreds or even thousands of times greater than what we observe in our galaxy today. This starburst phase will create a new generation of massive, brilliant stars that burn hot and die young, enriching the merged galaxy with heavy elements forged in their cores and scattered in their explosive deaths. What will happen to our solar system during this cosmic collision? The answer depends on where we're located within the Milky Way when the merger begins. Currently orbiting about 26,000 light-years from the galactic center, our Sun and its planets have roughly equal chances of 3 possible fates. We might be thrown outward into the extended halo of the merged galaxy, where we would witness the collision from a distance as a spectacular celestial display. Alternatively, we could be pulled inward toward the galactic core, entering a region of higher stellar density and more frequent close encounters with other stars. Or we might simply find ourselves in a new stable orbit within the merged galaxy, experiencing minimal disruption beyond the dramatically altered night sky. Earth itself, if it still exists, faces additional challenges during this period. By the time the galactic collision begins, our planet will already be experiencing the effects of our Sun's increasing luminosity. As stars like our Sun age, they gradually grow brighter, making Earth progressively warmer over billions of years. Within about 1 billion years from now, long before the galactic collision, Earth's oceans will begin to evaporate, making our planet increasingly inhospitable. By the time Andromeda looms large in our sky, Earth may already be a barren, Venus-like world, having lost its water and much of its atmosphere to the sun's increasing heat. If humanity or its evolutionary descendants still exist at this distant future time, they will likely have migrated to more distant planets or moons in our solar system, or perhaps to other star systems entirely. From these new vantage points, they would witness the collision as an unparalleled astronomical spectacle unfolding over millions of years. The night sky would be transformed from one dominated by the Milky Way's familiar band to a chaotic panorama filled with bright stars and glowing nebula in all directions. The boundaries between the original galaxies would blur and eventually disappear as their stars intermingle in a new galactic configuration. The collision process won't be a single event, but rather a series of encounters spanning hundreds of millions of years. After their first close pass, the two galaxies will swing away from each other, stretching into elongated shapes by their mutual gravitational attraction. But like two objects connected by an elastic band, they cannot escape each other's pull. They will curve back for a second, more direct encounter, losing energy through dynamical friction as their stars and gas clouds interact. With each pass, the galaxies will become more thoroughly mixed, their relative motion dampened by these interactions. Eventually, after perhaps 5 or 6 encounters over the course of 1 to 2 billion years, the galaxies will settle into a single, stable configuration. The beautiful spiral structures that once defined both the Milky Way and Andromeda will be gone, replaced by a new type of galaxy altogether. Astronomers predict that the merged galaxy, which they have preemptively named Milkomeda, will be an elliptical galaxy, a rounder, more three-dimensional distribution of stars lacking the distinctive spiral arms of its progenitors. This transformation from spiral to elliptical is common in galactic mergers. The ordered rotational motion that maintains spiral structures is disrupted by the gravitational chaos of the collision, converting that organized energy into random motion. The stars that once traveled in nearly circular orbits around their respective galactic centers will adopt new, more eccentric paths through the merged galaxy. This randomization of stellar orbits creates the characteristic ellipsoidal shape of elliptical galaxies. At the heart of Milkomeda, an even more dramatic event will unfold. The supermassive black holes that once occupied the centers of the Milky Way and Andromeda, objects with masses of 4 million and 100 million solar masses respectively, will themselves begin a gravitational dance. Initially separated by thousands of light years, these behemoths will gradually spiral toward each other as they lose energy through interactions with surrounding stars and gas. As the black holes approach within a few light years of each other, their gravitational influence will eject stars from the galactic center, creating a partially empty core. Within this cleared region, the black holes will continue their approach, eventually coming close enough for relativistic effects to take over. In their final merger, these objects will release an enormous amount of energy in the form of gravitational waves, ripples in the fabric of space-time itself that travel outward at the speed of light. This gravitational wave emission will carry away the equivalent of millions of solar masses of energy, making it one of the most energetic events in the history of the merged galaxy. The collision between the Milky Way and Andromeda won't occur in isolation. Our local group contains dozens of smaller galaxies that will be affected by the merger of its two largest members. The Triangulum Galaxy, or Messier 33, with its 40 billion stars, may join the collision, creating a three-way merger. Numerous dwarf galaxies, some already in orbit around the Milky Way or Andromeda, will be integrated into the new elliptical galaxy. The small and large Magellanic Clouds, irregular dwarf galaxies currently orbiting the Milky Way, may be torn apart by the changing gravitational landscape or may find new, stable orbits within the merged system. By the time Milkomeda reaches its final stable configuration, some 6 to 7 billion years from now, it will have incorporated most of the smaller galaxies in the local group. The result will be a massive elliptical galaxy containing well over 1 trillion stars, dominating the local cosmic neighborhood. This transformation represents a fundamental shift in the evolutionary trajectory of our galactic environment, from one characterized by separate spiral structures to a single, more homogeneous stellar distribution. The birth of Milkomeda will also mark a turning point in the star formation history of our local universe. Spiral galaxies like the Milky Way and Andromeda are still actively forming new stars, with gas-rich disks providing the raw material for stellar nurseries. Elliptical galaxies, in contrast, typically have lower star formation rates, having consumed or ejected much of their gas in the merger process. After an initial burst of star formation during the collision, Milkomeda will settle into a more quiescent phase, producing fewer new stars as the available gas is depleted. This transition has profound implications for the potential of life in the far future. New stars mean new planetary systems and new opportunities for life to emerge and evolve. As star formation rates decline in the post-merger galaxy, these opportunities will become progressively rarer. The elliptical galaxy phase can be thought of as a kind of cosmic middle age, still vibrant but past its prime in terms of creating new worlds where life might gain a foothold. Perhaps most sobering is the realization that this entire epic collision, spanning billions of years and encompassing over 1 trillion stars, will itself be just a prelude to even grander cosmic changes. By the time Milkomeda completes its formation, the universe will be nearly 20 billion years old, but this represents just a small fraction of cosmic time to come. The newly formed elliptical galaxy will continue to evolve for trillions of years more as its stars age, die, and occasionally form anew from recycled material. From the vantage point of cosmic history, we exist at a privileged moment, a time when large spiral galaxies still dominate our local group, when new stars are still forming at considerable rates, and when the evidence of the universe's evolution is still readily visible to us. Future astronomers, if any exist in the distant ages after the formation of Milkomeda, will observe a very different cosmic environment. The beautiful spiral structures that inspired generations of astronomers will be gone from their local universe, preserved only in observations of extremely distant galaxies. The rich history of galactic evolution that we can piece together from our observations will be increasingly obscured by the homogenizing effects of cosmic aging and merging. And yet, even as this galactic collision represents an end to the familiar structures we observe today, it also marks a new beginning, the birth of a galaxy unlike either of its progenitors, with its own unique evolutionary path stretching into the far future. This cycle of endings and beginnings characterizes the universe at all scales, from the death and birth of stars to the merging and formation of galaxies. The collision of the Milky Way and Andromeda reminds us that change is the only constant in the cosmos, operating on timescales far beyond human experience. As we contemplate this coming collision, we are confronted with the limits of our temporal perspective. The merger of these galaxies will unfold over a period more than 20 times longer than the entire history of life on Earth. No single human generation, indeed no single species, will witness this event from beginning to end. Yet through science, we can transcend these limitations, piecing together the story of our galaxy's future from the clues visible to us today. The Andromeda-Milky Way collision represents just the beginning of our journey through cosmic time. As spectacular as this merger will be, it pales in comparison to the even more dramatic events that await our universe in the far more distant future. From the death of our sun to the evaporation of black holes and beyond, the cosmos holds wonders that stretch the limits of human imagination. And as we turn our attention to these even more distant cosmic futures, we move from events that directly affect our galactic home to transformations that will reshape the very fabric of reality itself. 6 billion years. Its steady light and heat have made life possible on our planet, driving photosynthesis, powering our climate, and providing the energy that fuels nearly every ecosystem on Earth. Each day, the sun bathes our planet in more energy than humanity consumes in an entire year. This reliable influx of solar radiation has shaped everything from our planet's atmosphere to the biological rhythms that govern life. The 24-hour cycle of day and night, the seasonal patterns that drive migration and reproduction, even the very chemistry of our atmosphere, all are direct responses to the sun's influence. To human perception, the sun appears unchanging, rising and setting with reassuring consistency across the generations. Ancient civilizations worshipped it as a deity, recognizing its fundamental importance to life long before understanding its true nature. Egyptian pharaohs claimed descent from Ra, the sun god. Stonehenge was carefully aligned to track the sun's movement across the sky. The Aztec calendar stone centered on Tonatiuh, the solar deity who required sacrifice to continue his daily journey. This reverence reflected an intuitive understanding of our total dependence on solar energy, a relationship that modern science has only clarified and deepened. Yet this apparent permanence is an illusion born of our brief lives. The sun, like all stars, has a finite lifespan. It was born from a collapsing cloud of gas and dust. It ages through predictable stages of stellar evolution, and eventually it will die, transforming into something unrecognizable from its current state. This life cycle, though incomprehensibly long by human standards, is as certain as the daily sunrise. The sun currently exists in what astronomers call the main sequence phase of stellar evolution, a period of stability where the inward pull of gravity is perfectly balanced by the outward pressure generated by nuclear fusion in its core. Every second, the sun converts approximately 600 million tons of hydrogen into helium through this fusion process, releasing the energy equivalent of 100 billion nuclear bombs, 6 billion years of existence, 1% over geological timescales. Such stability has provided the consistent conditions necessary for life to evolve and thrive on Earth. But this equilibrium cannot last forever. In roughly 5 billion years, the hydrogen fuel in the sun's core will be exhausted, initiating a series of dramatic transformations that will ultimately end our star's life. To understand the sun's future, we must first appreciate its current state. Our star is classified as a G-type main sequence star, often called a yellow dwarf, though its actual color is white. 86% of all the mass in our solar system. Its core, where fusion occurs, reaches temperatures of 15 million degrees Celsius and densities 150 times that of water. Surrounding this core is the radiative zone, where energy slowly diffuses outward, followed by the convective zone, where massive currents of plasma circulate like water boiling in a pot. The sun's visible surface, the photosphere, has a relatively cool temperature of 5,500 degrees Celsius and gives way to the chromosphere and finally the extended tenuous corona that can reach temperatures of over 1 million degrees Celsius. The sun's evolutionary trajectory is not unique. Astronomers have observed stars at every stage of development across the galaxy, from newly formed protostars, still gathering material from their surrounding clouds, to ancient stellar remnants like white dwarfs. By studying these diverse stellar populations and applying our understanding of nuclear physics, scientists have constructed detailed models of how stars evolve. These models allow us to predict with remarkable confidence what will happen to our sun in the coming billions of years. The first signs of our aging sun will become apparent long before its final death throes. Even now, the sun is gradually becoming brighter as helium accumulates in its core. 6 billion years ago, it shone approximately 30% dimmer than it does today. This gradual brightening continues as a natural consequence of stellar aging. Helium, the product of hydrogen fusion, is denser than hydrogen and causes the core to contract slightly. This contraction raises the core temperature, accelerating the fusion of the remaining hydrogen around the helium core. The result is a steady increase in the sun's luminosity, about 10% every billion years. Geological evidence shows that Earth had liquid water and moderate temperatures, even when the sun was significantly dimmer early in our planet's history. Complex feedback mechanisms involving greenhouse gases, particularly carbon dioxide and methane, must have compensated for the lower solar output, keeping Earth's climate relatively stable over billions of years. These same feedback systems will face increasing challenges as the sun continues to brighten, eventually reaching a point where they can no longer maintain temperatures compatible with complex life. This seemingly modest brightness increase has profound implications for Earth. Our planet currently exists in what astronomers call the habitable zone around the sun, the region where temperatures allow water to exist as a liquid on a planet's surface. As the sun brightens, the habitable zone will gradually move outward, and Earth will find itself increasingly close to its inner edge. In approximately 1 billion years, the sun will be about 10% brighter than it is today, raising Earth's average temperature and accelerating the water cycle. This will enhance weathering of surface rocks, which will draw down carbon dioxide from the atmosphere. Carbon dioxide, though notorious as a greenhouse gas in our current climate concerns, is actually essential for plant life and for maintaining Earth's long-term temperature stability. As atmospheric carbon dioxide levels drop due to increased weathering, plants will struggle to perform photosynthesis. 1 billion years, atmospheric carbon dioxide will drop below the threshold needed for C3 photosynthesis, which is used by most plants. Only organisms using more efficient carbon fixation methods will survive. 5 billion years from now, Earth's oceans will begin to evaporate as surface temperatures rise above 50 degrees Celsius in the tropics. These changes will occur during what is still considered the Sun's main sequence lifetime, long before it enters its true giant phase. 5 billion years from now, surface conditions on Earth will likely resemble modern Venus, with all water vapor trapped in the upper atmosphere and surface temperatures exceeding 100 degrees Celsius globally. Complex life as we know it will have long since disappeared, though extremophile microorganisms might persist in specialized niches. The Sun's true transformation begins about 5 billion years from now, when the hydrogen fuel in its core is finally exhausted. At this point, the core, now composed primarily of helium, no longer generates the fusion energy needed to counteract gravity. Without this outward pressure, the core begins to collapse under its own weight, raising its temperature and density. This collapsing core triggers a new phase of hydrogen fusion in a shell surrounding the helium center. This shell burning produces more energy than the previous core fusion, causing the Sun's outer layers to expand dramatically. Our star will begin to swell, its diameter increasing at an accelerating rate as it transitions from a main sequence star to a red giant. During this phase, the Sun's surface temperature will cool to around 3,500 degrees Celsius, shifting its color from white-yellow to a deep orange-red. Despite this cooler surface, the Sun's total luminosity will increase substantially due to its much larger size. The expanding Sun will first engulf Mercury, the closest planet. This innermost world, a barren, cratered body with a diameter of just 4,880 kilometers, already experiences extreme conditions due to its proximity to the Sun. Its day side reaches temperatures of 430 degrees Celsius, hot enough to melt lead, while its night side plunges to minus 180 degrees Celsius. Such extremes will pale in comparison to what awaits this tiny world as the Sun expands. As the bloated red giant's outer atmosphere reaches Mercury's orbit, the planet will at first experience increasing drag as it moves through the thin solar material. This friction will cause its orbit to decay, sending it spiraling inward toward denser regions of the Sun. The intense heat will vaporize Mercury's surface layers, creating a comet-like tail that stretches behind it in its ever-tightening orbital path. Eventually, the tiny world will be completely vaporized as it plunges into the increasingly tenuous outer layers of the expanding star. The energy of Mercury's orbital motion will transfer to the Sun's material through friction, causing turbulence in the stellar atmosphere and potentially accelerating Mercury's destruction. Astronomers studying other solar systems have detected evidence of planets being consumed by their parent stars, suggesting this fate is relatively common across the universe. Venus, the second planet, faces a similar fate. Within a few million years of Mercury's demise, the Sun's continually expanding atmosphere will reach Venus's orbit. The planet that already suffers surface temperatures of 462 degrees Celsius under a crushing atmosphere will be enveloped by the far more extreme conditions of the Sun's outer regions. Like Mercury, Venus will spiral inward due to drag forces, eventually breaking apart and becoming fully incorporated into the Sun. The fate of Earth hangs in a delicate balance during this phase. In the early calculations of the Sun's evolution, scientists predicted that Earth would be engulfed just like its inner neighbors. However, more recent models that account for mass loss from the Sun during its giant phase suggest a different outcome. As the Sun expands, it will also lose mass through powerful stellar winds. This mass loss weakens the Sun's gravitational pull, allowing Earth's orbit to spiral gradually outward. Current models suggest that the Earth might escape direct engulfment by the thinnest of margins, perhaps by just a few million kilometers. But this technical survival would be cold comfort for our planet. Even if Earth avoids being physically swallowed by the expanding sun, it will be subjected to temperatures that will melt its surface into a magma ocean. Earth's atmosphere will be stripped away by intense solar radiation, and any oceans that somehow survived the earlier heating phases will instantly vaporize. Our planet, if it survives at all, will be reduced to a scorched, airless rock, perhaps resembling a larger version of Mercury as we know it today. The red giant phase represents the beginning of the end for the Sun, but it is far from a simple or brief conclusion. The Sun will exist as a red giant for approximately 1 billion years, undergoing several distinct phases during this time. Initially, as the hydrogen shell burns around the inert helium core, the Sun will expand to about 170 times its current diameter, large enough to reach somewhere between the orbits of Venus and Earth. As the helium core continues to contract and heat up, it will eventually reach the critical temperature of 100 million degrees Celsius needed to fuse helium into carbon. This ignition won't occur gradually, but will instead begin with a dramatic event called the helium flash, a runaway fusion reaction that will release as much energy in a few minutes as the entire Milky Way galaxy. Despite this enormous energy production, most of it will be absorbed by the Sun's own matter rather than being radiated into space, making the helium flash invisible to any hypothetical external observers. After the helium flash, the Sun will briefly shrink to about 10 times its current size as the new fusion process temporarily stabilizes its structure. This contraction occurs because helium fusion generates more energy per reaction than hydrogen fusion, providing greater support against gravity with less expansion needed. The Sun will shine with a luminosity roughly 50 times its current output, but concentrated in a smaller sphere, resulting in a higher surface temperature of about 4,200 degrees Celsius, giving it a yellow-orange appearance rather than the deep red of its earlier giant phase. During this phase, known to astronomers as the horizontal branch, due to how stars in this state appear on temperature-luminosity diagrams, the Sun will fuse helium in its core and hydrogen in a shell, with its surface temperature increasing slightly. The helium fusion process, called the triple alpha process, converts 3 helium nuclei into 1 carbon nucleus, with occasional further reactions producing oxygen. These elements, carbon and oxygen, will form the primary components of the Sun's eventual stellar remnant. However, this stability won't last. Within about 100 million years, the core helium will be exhausted, leading to another contraction and heating phase. Without the energy from helium fusion to counter gravity, the core will once again collapse, heating up the surrounding layers. The Sun will then begin to fuse helium in a shell around a newly formed carbon-oxygen core, causing it to expand once again to an even larger red giant. Astronomers refer to this second expansion as the asymptotic giant branch phase, where the star approaches its maximum possible size before losing its outer envelope entirely. In this second ascent of the red giant branch, sometimes called the asymptotic giant branch phase, the Sun may reach over 200 times its current diameter, extending well beyond Earth's orbit. During this phase, the Sun will experience thermal pulses, cyclical expansions and contractions driven by instabilities in the helium-burning shell. These pulses will cause the Sun to periodically brightening by factors of 5 to 10. The later stages of the red giant phase are characterized by increasing instability. The Sun will develop powerful stellar winds, ejecting matter into space at rates up to 1/1,000,000th of a solar mass per year. Over time, these winds will blow away the Sun's entire outer envelope, leaving behind only the hot, dense core. The ejected material will expand outward at speeds of 10 to 20 kilometers per second, forming a shell of gas and dust around the dying star. As the Sun's outer layers disperse into space, its hot core will be gradually revealed. With surface temperatures reaching 100,000 degrees Celsius, this stellar remnant will emit intense ultraviolet radiation that will cause the surrounding ejected material to glow. This glowing shell of expanding gas, illuminated by the hot core, is what astronomers call a planetary nebula, a misleading name from early astronomers who thought these objects resembled planets in their telescopes. Planetary nebulae are among the most beautiful objects in the universe. Each one is unique, with shapes ranging from simple spheres to complex structures with rings, lobes, or butterfly-like forms. The Sun's planetary nebula might take any of these shapes, depending on factors like rotation, magnetic fields, and the presence of companion objects. Whatever its shape, this nebula will be visible across thousands of light years, a cosmic monument marking the Sun's passing. The nebula phase is relatively brief in astronomical terms, lasting only about 50,000 years before the ejected material disperses too widely to be visible. What remains after the nebula fades is the Sun's exposed core, a white dwarf star. Composed primarily of carbon and oxygen, this remnant will contain about 54% of the Sun's original mass, compressed into a sphere roughly the size of Earth. This incredible density, about 1 million times that of water, results from a state of matter where electrons are compressed as tightly as quantum mechanics allows, without collapsing into neutrons. The white dwarf Sun will shine with a bright blue-white color due to its extremely high surface temperature of around 100,000 degrees Celsius. However, it will be much dimmer than the current Sun despite this high temperature because of its much smaller size. With no fusion energy being generated, the white dwarf will simply radiate its stored thermal energy into space, gradually cooling over trillions of years. This cooling process follows a predictable pattern. After about 1 billion years, the white dwarf's temperature will drop to around 5,000 degrees Celsius, similar to the current Sun's surface, but from a much smaller object. By 10 billion years after its formation, it will cool to about 1,500 degrees Celsius, glowing a dull red. After hundreds of billions of years, the white dwarf will cool enough that its atmosphere may crystallize, essentially turning the Sun into a diamond-like sphere floating in the darkness of space. Eventually, after trillions of years, the white dwarf will cool to the temperature of the surrounding space, just a few degrees above absolute zero. At this point, it will become a black dwarf, a cold, dark ball of carbon and oxygen, invisible except by its gravitational influence. However, this final stage is theoretical, as the universe is not yet old enough for any white dwarfs to have cooled completely. Even the oldest white dwarfs in our galaxy still retain significant heat from their formation. The transformation of our Sun from its current state to a black dwarf spans a time frame almost incomprehensible to human perception, from our present moment to more than 1 trillion years in the future. During this vast period, the Sun will have changed from a stable yellow-white star to a bloated red giant, then to a hot planetary nebula core, followed by a cooling white dwarf, and finally to a cold, dark remnant. Each of these stages represents a distinct physical process governed by the interplay between gravity, nuclear physics, and the quantum behavior of matter under extreme conditions. Could humanity survive this solar transformation? The prospect raises profound questions about the longevity of our species and the limits of technological adaptation. With sufficient advancement, it's conceivable that our descendants might migrate to more distant planets or moons as the Sun brightens. The outer solar system, particularly moons like Europa or Titan, might become more habitable as they warm up during the Sun's late main sequence and early red giant phases. Europa, currently covered in a thick ice shell concealing a deep liquid ocean, might transform into a water world as the ice melts away under increased solar radiation. Titan, with its thick atmosphere and hydrocarbon lakes, might warm enough for liquid water to exist on its surface, potentially creating conditions where Earth-like biochemistry could function. Some scientists have proposed even more ambitious survival strategies. Freeman Dyson and other futurists have speculated that advanced civilizations might dismantle planets to construct Dyson swarms, vast arrays of habitats orbiting the star at various distances, each positioned to receive optimal levels of radiation as the Sun evolves. Others suggest the possibility of stellar engineering, actively removing mass from the Sun to extend its main sequence lifetime or moderate its expansion during the red giant phase. The ultimate solution would likely involve interstellar migration. If humanity exists in any recognizable form billions of years from now, it would almost certainly have spread to other star systems. Astronomers have already identified numerous exoplanets orbiting younger stars, with billions of years of stable conditions ahead of them. By the time our Sun begins its final expansion, an advanced human civilization might have established itself around hundreds or thousands of other stars, viewing the death of their original sun with scientific interest rather than existential dread. However, the red giant phase itself would likely render the entire inner solar system uninhabitable, forcing any humans who remain to either move to interstellar space or develop extraordinary protective technologies. Even the outer planets would face challenges from the increased solar wind and radiation during the sun's unstable later phases. The most likely scenario is that Earth will be abandoned long before the sun reaches its red giant phase, preserved in memory and records, but no longer humanity's home. The death of the sun represents one of the most profound changes our solar system will experience, transforming the environment that has fostered Earth's evolution for billions of years. Yet it is also part of a greater cosmic cycle. The material ejected during the sun's red giant phase will eventually mix with the interstellar medium, potentially becoming part of new star systems in the future. The carbon, nitrogen, and oxygen atoms created through fusion in the sun's interior will form an essential part of the raw materials for future planets and perhaps future life. In this way, the sun's death contains the seeds of new beginnings. The same processes that will eventually destroy our solar system as we know it also enrich the galaxy with the elements necessary for planets and life. Our sun's demise, though spectacular and ultimately fatal for Earth, represents just one small part of the ongoing cycle of stellar birth, life, and death that drives cosmic evolution. As dramatic as the sun's death will be, it represents a relatively gentle stellar ending. More massive stars meet far more violent fates, exploding as supernovae that momentarily outshine entire galaxies. These cataclysmic events create the heaviest elements in the universe and propagate shockwaves that can trigger the formation of new stars. As we consider the sun's relatively peaceful transition to a white dwarf, we should also contemplate these more dramatic stellar deaths that shape the chemistry and structure of galaxies, including our own. It is to these cosmic fireworks that we now turn our attention. While our sun will meet its end in the relatively gentle transformation to a white dwarf, other stars throughout the universe face far more dramatic fates. For stars substantially more massive than our sun, death comes not as a gradual fading, but as a cataclysmic explosion of almost unimaginable power, a supernova. These stellar detonations rank among the most energetic events in the cosmos, briefly outshining entire galaxies and dispersing newly forged elements across interstellar space. Though human astronomers have observed supernovae in distant galaxies and historical records document a few such explosions in our own Milky Way, the most spectacular stellar explosions predicted by astrophysics lie in our future, cosmic fireworks that will occur long after humanity has vanished from the stage. To understand these stellar cataclysms, we must first recognize that stars are cosmic balancing acts. Throughout a star's life, the inward pull of gravity is counteracted by the outward pressure generated by nuclear fusion in its core. For stars like our Sun, with masses up to about 8 times solar mass, this balance can be maintained through several stages of fusion, from hydrogen to helium, and briefly helium to carbon and oxygen. But stars cannot fuse carbon and oxygen in their cores without significantly more mass and the extreme temperatures and pressures that come with it. More massive stars follow a different evolutionary path. With their stronger gravitational compression, these stellar giants can reach core temperatures high enough to fuse progressively heavier elements. After exhausting their core hydrogen, they fuse helium not in a flash, but in a controlled manner lasting millions of years. This is followed by carbon fusion, then neon, oxygen, and finally silicon. Each successive stage burns faster than the last, as the energy yield decreases and the star must compensate by increasing its reaction rate. While hydrogen fusion can power a star for billions of years, silicon fusion lasts mere days before the core is converted primarily to iron and related elements. Iron marks the end of the line for fusion energy production. Unlike lighter elements, fusing iron does not release energy, but actually requires energy input. With iron accumulating in its core and no new energy source to counteract gravity, a massive star faces imminent catastrophe. 4 solar masses. At this point, even the pressure of electrons cannot prevent collapse, and the core begins to implode. This collapse occurs with breathtaking speed. In less than a second, the iron core shrinks from a diameter of several thousand kilometers to a mere tens of kilometers. As protons and electrons are crushed together by the extreme pressure, they form neutrons and emit neutrinos, ghostly particles that barely interact with normal matter. Despite their elusive nature, neutrinos carry away about 99% of the supernova's energy, preceding the visible explosion by several hours. The collapse halts only when the core reaches nuclear density, where the strong nuclear force creates a new form of pressure. The sudden halt of the collapse creates a rebound shockwave that begins to propagate outward. However, computer simulations show that this initial shock typically stalls before reaching the star's surface. The explosion is ultimately powered by a small fraction of the escaping neutrinos, which deposit enough energy to reinvigorate the shock and drive it through the outer layers of the star. This neutrino heating remains an active area of research, with three-dimensional simulations only recently becoming sophisticated enough to consistently produce successful explosions. When the shockwave finally reaches the star's surface, the real spectacle begins. The star brightens by a factor of several billion in a matter of hours, reaching a luminosity that can rival its entire host galaxy. The surface temperature soars to billions of degrees, driving a blast of radiation across the electromagnetic spectrum. If such an explosion occurred within our Milky Way galaxy, it would be visible even in daylight, potentially casting shadows at night if close enough. However, the last such galactic supernova visible to the naked eye occurred in 1604, Kepler's supernova, before the invention of the telescope. Supernovae come in different varieties, classified by their light curves and spectral features. The type described above, resulting from the core collapse of a massive star, is called a Type II supernova if hydrogen is detected in its spectrum, or a Type Ib-C if the star had previously lost its hydrogen envelope. Another variety, Type Ia, results from a completely different mechanism, a white dwarf in a binary system accumulating matter from its companion until it reaches the Chandrasekhar limit, triggering a thermonuclear explosion that completely destroys the star. Among these varieties, some supernovae stand out for their exceptional brightness and energy output. Astronomers have discovered what they call superluminous supernovae that shine 10 to 100 times brighter than typical events. These rare explosions may result from extremely massive stars, unusual explosion mechanisms, or additional energy sources, such as a rapidly spinning neutron star or black hole formed in the explosion. One such object, designated SN 2006 GY, radiated more energy than most galaxies for several months, suggesting an original star of perhaps 150 solar masses. Even more extreme are the hypothetical hypernovae linked to gamma-ray bursts, the most energetic explosions observed in the universe. These events are thought to occur when massive, rapidly rotating stars collapse to form black holes. Rather than exploding symmetrically, these stars channel much of their energy along their rotational axes, creating narrow jets of particles moving at nearly the speed of light. If one of these jets happens to point toward Earth, we observe a brilliant flash of gamma rays followed by a longer-lasting afterglow across multiple wavelengths. Within our own galaxy, several stars are candidates for future supernovae, with Betelgeuse perhaps the most famous. Located about 700 light-years from Earth in the constellation Orion, this red supergiant has already exhausted its core hydrogen and expanded to more than 1,000 times the Sun's diameter. If placed at the center of our solar system, Betelgeuse would engulf all the planets out to Jupiter. Its distinctive reddish color, visible to the naked eye as Orion's right shoulder, comes from its relatively cool surface temperature of about 3,300 degrees Celsius. Betelgeuse's eventual explosion has captured public imagination, partly because it's relatively close and would create a spectacular sky show visible even in daylight. 6 billion-year-old Sun, but is already in the late stages of its life due to its much higher mass of about 11 to 12 times that of the Sun. The exact timing of Betelgeuse's demise remains uncertain. It could explode tomorrow or 100,000 years from now. Recent observations showing unusual dimming in 2019 to 2020 created brief excitement that an explosion might be imminent, but this was later attributed to a combination of normal stellar pulsations and a dust cloud partially obscuring the star. When Betelgeuse does eventually explode, It will shine as brightly as the half moon for several months, visible even during daylight. At night, it would be bright enough to cast shadows and be easily visible through light pollution that obscures most stars. Despite its proximity, Betelgeuse poses no danger to Earth. At 700 light-years distance, the explosion's energy will have dissipated enough that neither its radiation nor any ejected material will significantly affect our planet. Some scientists suggest the increased ultraviolet radiation might have minor effects on Earth's upper atmosphere, potentially disrupting radio communications temporarily, but would not threaten life or climate systems. While Betelgeuse is the most well-known supernova candidate visible to the naked eye, other stars in our galaxy may explode even sooner. Eta Carinae, a peculiar stellar system about 7,500 light-years away in the southern constellation Carina, consists of at least 2 stars with a combined mass of more than 100 times that of the Sun. In the 1840s, it underwent a massive outburst called the Great Eruption, briefly becoming the second brightest star in the sky despite its much greater distance than Betelgeuse. This event ejected material equivalent to 10-15 solar masses, creating a distinctive hourglass-shaped nebula visible today through telescopes. Many astronomers believe Eta Carinae will explode as a supernova or even hypernova within the next 100,000 years, potentially triggering one of the most energetic stellar explosions in our galaxy's recent history. Another category of supernovae candidate stars includes Wolf-Rayet stars, extremely hot bright stars that have shed their outer hydrogen layers, exposing their helium-burning cores. The nearest example is Gamma Velorum, about 1,100 light-years away in the southern constellation Vela. These stars represent the final stage of evolution for some of the most massive stars in the universe, with surface temperatures reaching 50,000 to 150,000 degrees Celsius, many times hotter than our Sun. Their strong stellar winds blow at speeds of several thousand kilometers per second, causing them to lose mass at prodigious rates. This mass loss shapes the surrounding interstellar medium and contributes to the star's distinctive emission spectra. When Wolf-Rayet stars finally explode, they tend to produce type Ib or icy supernovae, lacking hydrogen in their spectra due to the prior loss of their outer envelopes. The rarity of observed supernovae in our galaxy might suggest they are uncommon events, but this is an illusion created by our brief observational history. Astronomers estimate that supernovae occur in the Milky Way at an average rate of 1 to 3 per century. The discrepancy between this rate and the small number actually observed throughout human history, only 5 to 7 definitive Milky Way supernovae have been recorded since 1000 CE, is explained by the fact that many supernovae are obscured by interstellar dust. Our galaxy's disk is filled with dust clouds that can block visible light, hiding explosions that occur on the opposite side of the galactic center or within dusty spiral arms. Modern astronomical techniques using infrared, radio, and high-energy observations can detect some of these hidden explosions, but many still go unnoticed from our vantage point. The effects of these stellar explosions extend far beyond the dramatic light shows they produce. Supernovae are cosmic forges that create and disperse heavy elements throughout the universe. During both the star's life and its explosive death, nuclear fusion creates elements heavier than hydrogen and helium, the only elements formed in significant quantities during the Big Bang. Elements up to iron are synthesized through fusion during the star's life, while elements heavier than iron are primarily created during the explosion itself through processes like rapid neutron capture, the R process. Without supernovae, the universe would lack most of the chemical diversity we observe today, including elements essential for planets and life. When a supernova explodes, it launches these newly formed elements into interstellar space at speeds of thousands of kilometers per second. This enriched material eventually mixes with existing gas clouds, increasing their metallicity, the proportion of elements heavier than hydrogen and helium. When these enriched clouds collapse to form new stars and planets, they incorporate these heavy elements. The calcium in our bones, the iron in our blood, the oxygen we breathe, and the carbon in our DNA were all forged in ancient stars and dispersed by supernovae billions of years ago. As astronomer Carl Sagan famously noted, "We are made of star stuff," a poetic truth rooted in the science of stellar nucleosynthesis and supernova explosions. Beyond enriching the interstellar medium with heavy elements, supernovae play a crucial role in triggering new star formation. The shock waves from these explosions compress nearby gas clouds, potentially initiating their collapse into new stellar nurseries. There is evidence that our own solar system may have formed in response to a nearby supernova, which not only triggered the collapse of the molecular cloud that became our sun and planets, but also injected freshly synthesized radioactive isotopes. Trace amounts of these isotopes, such as aluminum-26, have been detected in meteorites, providing a chemical signature of our solar system's explosive origin. Looking to the far future, the rate of supernovae in our galaxy and throughout the universe will change dramatically. Star formation in the Milky Way has already declined from its peak about 10 billion years ago, and this trend will continue as the available gas for forming new stars is gradually depleted. Fewer new stars means fewer massive stars, which translates to a declining supernova rate over the coming billions of years. Computer simulations suggest that by 100 billion years from now, the supernova rate in our local group of galaxies will be less than 1% of the current rate. Eventually, as star formation ceases entirely, supernovae will become increasingly rare events. The last core collapse supernova, those resulting from massive stars, will occur within about 100 billion years, after the final generation of massive stars completes its relatively short life cycle. Type Ia supernovae, those caused by white dwarf explosions in binary systems, will continue for much longer, perhaps for trillions of years, as white dwarfs slowly migrate through the aging galaxy and occasionally find companions to trigger their detonation. But even these will eventually cease, as the supply of white dwarfs in suitable binary arrangements is gradually exhausted. The cessation of supernovae will mark a profound transition in cosmic evolution. Without these explosions to stir the interstellar medium and trigger new star formation, the universe will become increasingly quiescent. The dynamic, chemically evolving cosmos we observe today will give way to a more static reality, where existing stars gradually exhaust their fuel and fade away without replacement. This transition represents one of the key milestones in the universe's aging process, the end of cosmic renewal through stellar explosions. Yet even as we contemplate this distant future, where supernovae no longer light up the cosmos, we should recognize the extraordinary fortune of our existence in the current epoch. We live in a universe where these stellar explosions are still relatively common, continuing to forge new elements and trigger the formation of new stars and solar systems. The heavy elements that make up our planet and our bodies are the legacy of ancient supernovae that occurred before our sun formed, connecting us directly to this ongoing cycle of stellar birth, death, and rebirth. The most energetic supernovae, those rare events that momentarily outshine entire galaxies, remain largely theoretical for us. Though astronomers have observed particularly bright explosions in distant galaxies, the truly spectacular events predicted by our understanding of stellar physics, hypernovae, pair instability supernovae, and collapsar events associated with gamma-ray bursts, are rare enough that humanity may never witness the most extreme examples in our cosmic neighborhood. These are the cosmic fireworks that future observers, if any exist, might witness across the immense gulf of time that separates us from the universe's distant future. When we observe the remnants of past supernovae, the beautiful expanding shells of gas visible in astronomical images, we see only the aftermath of these cosmic explosions. The Crab Nebula, observed and recorded by Chinese astronomers in 1054 CE, shows us what remains nearly 1,000 years after a massive star met its end. The more recent Cassiopeia A supernova remnant, whose light reached Earth about 340 years ago, offers a closer look at the early evolution of the debris from such an explosion. These remnants are like cosmic archaeological sites, preserving the history of stellar deaths for astronomers to study. The violent deaths of massive stars also leave behind exotic remnants, neutron stars or black holes. When the core of a massive star collapses, it can form a neutron star, essentially a giant atomic nucleus about 20 kilometers in diameter, but containing more mass than our Sun, composed almost entirely of neutrons. The density of these objects is almost incomprehensible. A teaspoon of neutron star material would weigh billions of tons on Earth. These stellar remnants often spin rapidly, sometimes making hundreds of rotations per second, and possess extremely strong magnetic fields. For the most massive stars, even the pressure of neutron degeneracy cannot halt the core collapse, and a black hole is formed, an object so dense that its gravitational pull prevents even light from escaping. These stellar mass black holes are the most common type in the universe, far outnumbering the supermassive black holes found at the centers of galaxies. Both neutron stars and black holes can announce their presence through interactions with companion stars or surrounding material, producing some of the most energetic phenomena observed in astronomy, including pulsars, magnetars, and microquasars. As we contemplate these violent stellar deaths and their exotic remnants, we recognize that they represent just one aspect of the universe's evolution. Even as supernovae become increasingly rare over cosmic time, other processes will continue to shape the cosmos. The mergers of neutron stars and black holes, detected through gravitational waves by modern observatories, will continue for trillions of years. Galaxies will complete their own life cycles of collision and merger, and the universe itself will continue its expansion, driven by the mysterious force we call dark energy. The transformation from our current star-forming epoch to the distant future, where supernovae no longer occur, represents a fundamental transition in cosmic history, from a universe of renewal and chemical evolution to one of gradual decay. This transition connects directly to our next topic: the formation and evolution of black holes, objects that will dominate the universe's extremely distant future long after the last stars have ceased to shine. These gravity wells in space-time, born from the deaths of the most massive stars, represent the next chapter in our cosmic story. In the cosmic hierarchy of extraordinary objects, nothing captivates our imagination quite like black holes, regions of space-time where gravity is so extreme that nothing, not even light, can escape once it crosses the event horizon. These cosmic singularities represent the ultimate fate of sufficient mass compressed into sufficiently small volumes, where the known laws of physics reach their limits and our understanding gives way to speculation. Though black holes evoke images of cosmic destroyers, inexorably consuming anything that ventures too close, they are also creative forces on the grandest scale, shaping galaxies, triggering star formation, and potentially seeding the universe with the heavy elements necessary for complex chemistry and life. The very concept of black holes emerged from theoretical physics long before any observational evidence confirmed their existence. In 1783, John Michell, an English natural philosopher, first proposed the idea of dark stars so massive that even light could not escape their gravitational pull. In 1915, Albert Einstein's general theory of relativity provided the mathematical framework that would later be used to describe black holes. Though Einstein himself was skeptical they could exist in reality. It wasn't until Carl Schwarzschild solved Einstein's field equations for a point mass that the first truly modern description of a black hole emerged, defining what we now call the Schwarzschild radius, the size of the event horizon for a non-rotating black hole. For decades, black holes remained mathematical curiosities rather than confirmed astrophysical objects. That changed in the latter half of the 20th century, as observations of unusual compact objects like Cygnus X1 provided strong indirect evidence for stellar mass black holes in binary systems. The discovery of quasars, extraordinarily bright galactic nuclei, pointed to the existence of supermassive black holes powering these cosmic beacons. By the early 21st century, the evidence had become overwhelming, culminating in the 2019 direct imaging of the shadow of the supermassive black hole at the center of galaxy M87 by the Event Horizon Telescope collaboration. As we peer into the distant cosmic future, black holes will become increasingly dominant features of our universe, outlasting stars, planets, and perhaps all other structures in existence. The simplest way to form a black hole is through the death of a massive star. As we explored in our discussion of supernovae, stars with initial masses greater than about 20 times that of our Sun face a catastrophic end. When such stars exhaust their nuclear fuel, their cores collapse under gravity's relentless pull. For slightly less massive stars, this collapse halts with the formation of a neutron star, essentially a giant atomic nucleus composed primarily of neutrons. 5 to 3 solar masses, no known force can resist the gravitational compression. The physics of this collapse is both elegant and terrifying. As the star's fusion processes cease to generate outward pressure, the core begins to implode under its own weight. Electrons are forced to combine with protons, forming neutrons and releasing ghostly particles called neutrinos that carry away enormous amounts of energy. For cores below the critical mass, neutron degeneracy pressure, a quantum mechanical effect preventing neutrons from occupying the same quantum states, can halt the collapse. Above this threshold, even this exotic pressure fails. The collapsing core continues to compress beyond the density of an atomic nucleus, theoretically reaching a point of infinite density and zero volume, a singularity, surrounded by a boundary called the event horizon, which marks the point of no return for matter and light. This boundary is not a physical surface, but a mathematical sphere where the escape velocity equals the speed of light. An outside observer would never see matter actually cross this boundary. Time dilation effects cause infalling objects to appear to slow and freeze at the horizon, their light increasingly redshifted until they fade from view. This stellar path to black hole formation continues throughout the universe today. In our Milky Way alone, astronomers estimate that one massive star explodes as a supernova every 50 to 100 years, with perhaps 1/3 of these events producing black holes rather than neutron stars. Most occur in distant parts of the galaxy, hidden from Earth by interstellar dust, but advanced gravitational wave detectors now allow us to detect black hole births throughout our local universe. Each detection represents the violent birth of a new black hole, another addition to the cosmic population of these extreme objects. One such stellar black hole may be forming right now in our cosmic neighborhood. In 2019, astronomers observed an unexpected dimming of Betelgeuse, a red supergiant star in the constellation Orion. While this particular event was later attributed to a dust cloud rather than an imminent explosion, Betelgeuse remains one of the most likely nearby stars to produce a supernova and potentially a black hole within the next 100,000 years. When this eventually occurs, the initial explosion will be visible from Earth even in daylight, appearing as bright as the moon for several weeks before gradually fading. If the collapsing core is massive enough, the supernova remnant will harbor a newly formed black hole roughly 10 times the mass of our Sun, but compressed into a region smaller than Manhattan. More dramatic black hole formation events occur when especially massive stars reach the end of their lives. Stars with initial masses exceeding 150 solar masses may experience a catastrophic instability in their cores. At the extreme temperatures reached during advanced fusion stages, energy becomes so concentrated that it spontaneously converts into matter-antimatter pairs, reducing the radiation pressure that supports the star against gravity. The resulting collapse triggers a runaway thermonuclear explosion that completely destroys the star in what astronomers call a pair instability supernova. Recent observations have revealed that stellar black holes can be significantly more massive than previously believed. In 2019, the LIGO-Virgo gravitational wave observatories detected the merger of two black holes with masses of 66 and 85 solar masses, producing a final black hole of about 142 solar masses. The larger of the initial black holes challenged theoretical models, which had suggested that stellar processes could not produce black holes with masses between approximately 65 and 120 solar masses due to pair instability effects in massive stars. This observation, designated GW190521, was remarkable not only for the masses involved, but for what it revealed about black hole formation. The mass gap between 65 and 120 solar masses exists in theory because stars massive enough to form such black holes should experience pair instability supernova, explosions so powerful they completely disrupt the star rather than leaving behind a black hole. Finding black holes in this forbidden range suggests either that our understanding of stellar evolution needs revision, or that these objects formed not directly from stars, but from previous generations of black hole mergers. 6 solar masses, lighter than any previously known black hole, and falling within what was thought to be another mass gap between the heaviest possible neutron stars and lightest possible black holes. This discovery, if confirmed, challenges our understanding of both neutron star physics and black hole formation mechanisms. The boundaries between these exotic objects may be fuzzier than previously thought, with implications for the total population of black holes in the universe. While stellar deaths represent the most common black hole formation mechanism in the current epoch, the universe's earliest black holes likely formed through different processes. In the first billion years after the Big Bang, regions of unusually high density in the primordial gas may have collapsed directly into black holes without first forming stars. These direct collapse black holes could have reached masses of tens of thousands to millions of solar masses very quickly, potentially explaining the puzzling existence of supermassive black holes observed in the early universe. Other theoretical mechanisms include the collapse of massive population 3 stars, the universe's first generation of stars, which contained no elements heavier than helium, or even exotic processes in the first seconds after the Big Bang that might have produced primordial black holes across a wide range of masses. The most massive black holes in existence are the supermassive varieties found at the centers of most large galaxies. Our own Milky Way harbors a black hole called Sagittarius A star, pronounced Sagittarius A star, with a mass of about 4 million times that of our Sun. While substantial, this is actually relatively modest compared to other galactic behemoths. The nearby Andromeda galaxy contains a black hole estimated at 100 to 240 million solar masses, while the record holders in the observable universe reach tens of billions of solar masses. 5 billion suns compressed into a region smaller than our solar system. Our understanding of Sagittarius A star has been transformed by decades of patient observation. Located approximately 26,000 light-years from Earth in the direction of the constellation Sagittarius, this black hole is not directly visible, even with our most powerful telescopes. Instead, astronomers have mapped its properties by tracking the orbits of stars in the galactic center. The most famous of these, designated S2, completes an elliptical orbit around the invisible mass every 16 years, approaching within just 17 light-hours at its closest approach, about 4 times the distance from our Sun to Neptune. 5% the speed of light. By precisely measuring the orbit of S2 and other stars in this central cluster, astronomers have determined the mass of the central object with high precision and shown that it must be contained within a volume so small that a supermassive black hole is the only plausible explanation. These observations, which earned the 2020 Nobel Prize in Physics for Reinhard Genzel and Andrea Ghez, provide some of the most compelling evidence for the existence of black holes and confirm Einstein's general theory of relativity in the strongest gravitational fields accessible to our observations. The Event Horizon Telescope's revolutionary image of the M87 black hole's shadow revealed another aspect of these supermassive objects, their surrounding environment. The glowing ring visible in the image is not the event horizon itself, which is by definition invisible, but superheated plasma in the accretion disk just outside the horizon, with the dark central region representing the shadow cast by the black hole against this background. The asymmetry in the ring's brightness confirms that the material is orbiting the black hole, with the Doppler-boosted radiation from the side moving toward us, appearing brighter than the receding side. How these galactic monsters formed remains an area of active research. The leading theory suggests they grew from smaller seed black holes, perhaps formed through the direct collapse mechanisms mentioned earlier, that subsequently accumulated mass by consuming gas, dust, stars, and even other black holes. The process would have begun in the early universe when galaxies were still forming, with early black holes growing rapidly by accreting material from their gas-rich surroundings. As galaxies merged over cosmic time, their central black holes would also ultimately merge, further increasing their masses. We can observe this growth process through the phenomenon of active galactic nuclei, AGN, galaxies with extraordinarily bright centers powered by matter falling into supermassive black holes. As gas spirals inward toward the black hole, it forms an accretion disk heated to millions of degrees by friction and compression. This superheated material releases enormous amounts of energy before crossing the event horizon, making AGN among the most luminous sustained energy sources in the universe. Quasars, the most extreme type of AGN, can outshine all the stars in their host galaxies combined. When we observe a quasar, we are witnessing the growth phase of a supermassive black hole, actively consuming material and increasing its mass. the future of black hole formation will evolve along with the changing universe. In the relatively near cosmic future, over the next few billion years, black hole formation will continue much as it does today, with massive stars collapsing at the ends of their lives and supermassive black holes growing through accretion and mergers. However, as star formation rates decline and galaxies exhaust their supplies of free gas, the creation of new stellar black holes will gradually decrease. By about 100 trillion years from now, the last main sequence stars will have exhausted their fuel and no new stellar black holes will form through the conventional supernova mechanism. Even after star formation ceases, black hole populations will continue to evolve through interactions and mergers. In the dense environments of galactic centers, black holes will occasionally pass close enough to each other to form gravitationally bound systems. Over time, these binary black holes will spiral closer together through the emission of gravitational waves, ripples in spacetime that carry away energy and angular momentum. The final merger of such a pair results in a more massive black hole, often with a substantial recoil velocity due to asymmetric gravitational wave emission. Astronomers have already observed dozens of such mergers through gravitational wave detectors, providing direct evidence that this process actively contributes to black hole evolution. Particularly interesting is the future of Sagittarius A star, our galaxy's central black hole. Currently, it is relatively quiet, accreting only small amounts of gas from its surroundings. 5 billion years from now, when the Andromeda Galaxy collides with the Milky Way, this cosmic collision will funnel large amounts of gas toward the galactic center, potentially triggering a quasar-like outburst as the black hole feasts on this new material. More significantly, the supermassive black holes from both galaxies will themselves eventually merge after a complex dance that may take billions of years to complete. This merger of supermassive black holes would release an enormous amount of energy in the form of gravitational waves. While even our most sensitive current detectors could not detect this event if it happened in a distant galaxy, future civilizations in the merged Milky Galaxy would experience it as a literal shaking of space-time. The final moments of the merger would release energy equivalent to billions of supernovae, though mostly in the form of gravitational waves rather than electromagnetic radiation. The resulting black hole would have a mass of over 100 million suns, dominating the central region of the newly formed elliptical galaxy. Beyond the merger of the Milky Way and Andromeda, the broader local group of galaxies, which includes dozens of smaller galaxies, such as the Triangulum Galaxy and the Magellanic Clouds, will gradually coalesce into a single massive elliptical galaxy over the next 100 billion years. Each constituent galaxy brings its own central black hole to this extended merger process, ultimately creating a single supermassive black hole, perhaps a billion times more massive than our Sun. This object will sit at the center of the merged galaxy long after the last stars have died, accreting any material that strays too close. On even longer timescales, black holes throughout the universe will grow through a process that seems counterintuitive: the evaporation of other black holes. In 1974, Stephen Hawking showed that black holes are not completely black, but emit a faint radiation due to quantum effects near their event horizons. This Hawking radiation causes black holes to gradually lose mass, with smaller black holes evaporating faster than larger ones. Over incomprehensibly long periods, from 10 to the power of 64 years for stellar mass black holes to 10 to the power of 100 years for supermassive ones, this process will cause most black holes to completely disappear. However, before this ultimate evaporation, another process may intervene. In the extremely dense environment of a dead galaxy's central regions, stellar remnants, including white dwarfs, neutron stars, and smaller black holes, will occasionally be captured by the central supermassive black hole. Each such capture increases the supermassive black hole's mass slightly, potentially offsetting the mass loss due to Hawking radiation. The result is that while smaller black holes will eventually evaporate, the largest supermassive black holes may continue to grow slowly, even in galaxies where no new stars form. This process creates a striking vision of the ultra-distant future, a universe where most matter has been incorporated into a relatively small number of extremely massive black holes. These objects would orbit each other at enormous distances in the otherwise empty void created by the continuing expansion of the universe. Occasionally, over timescales of trillions upon trillions of years, pairs of these black holes might meet and merge, creating even larger black holes. This process of hierarchical merging could, in theory, continue indefinitely, creating ever larger black holes in an otherwise increasingly empty universe. The formation mechanisms for these future black holes, then, will differ fundamentally from those operating today. Rather than forming primarily from collapsing stars, most new black holes in the distant future will result from the mergers of existing ones. As the universe ages, the black hole population will evolve toward fewer but more massive objects, with the total mass contained in black holes actually decreasing over time due to Hawking radiation. Eventually, even these merged giants will succumb to evaporation, though this process would take longer than the current age of the universe by factors of trillions or more. Another fascinating aspect of future black hole evolution involves their rotation. When a star collapses to form a black hole, conservation of angular momentum causes the black hole to spin, sometimes at significant fractions of the speed of light. Similarly, when black holes merge, the resulting object typically spins rapidly due to the orbital angular momentum of the initial pair. These spinning black holes, called Kerr black holes, after the physicist who first described them mathematically, have additional interesting properties beyond their non-rotating counterparts, including the creation of frame-dragging effects in the surrounding spacetime. In the most extreme cases, rapidly spinning black holes may power phenomena like relativistic jets, narrow beams of particles accelerated to nearly the speed of light along the black hole's rotational axis. These jets can extend for hundreds of thousands of light years, influencing gas dynamics and star formation across entire galaxies. While such active phases require a steady supply of infalling material, which will become increasingly scarce in the aging universe, brief episodes of activity might continue far into the future whenever a substantial object falls into an otherwise dormant black hole. The evolution of black holes also has profound implications for the information content of the universe. According to quantum physics, information cannot be destroyed, yet black holes appear to erase the distinctive characteristics of anything that falls into them. This apparent contradiction, known as the black hole information paradox, remains one of the most profound unresolved questions in theoretical physics. The resolution may lie in the nature of Hawking radiation, which some theories suggest must subtly encode information about everything that ever fell into the black hole. If true, the final evaporation of the last black holes in the distant future would release this encoded information back into the universe, preserving the fundamental principle of information conservation. For any hypothetical civilizations surviving into these distant epochs, black holes would represent not just objects of scientific interest, but potentially crucial resources. Some physicists have suggested that advanced civilizations might extract energy from rotating black holes through a process called the Penrose process, potentially powering computation and life even as conventional energy sources like stars disappear. The Penrose process, named after mathematician Roger Penrose, who first described it in 1969, exploits the peculiar region just outside a rotating black hole's event horizon called the ergosphere. Within this region, spacetime itself is dragged along with the black hole's rotation, making it impossible for objects to remain stationary relative to distant space. If a particle splits into two pieces in the ergosphere, with one piece falling into the black hole and the other escaping, the escaping piece can emerge with more energy than the original particle possessed, effectively extracting rotational energy from the black hole. More speculative is the possibility of using black holes as tools for computation or information storage. Theoretical physicist Seth Lloyd has proposed that the ultimate computational device might be a black hole, using quantum gravitational effects to process information at the maximum rate allowed by the laws of physics. Other researchers have suggested that the event horizons of black holes might serve as a kind of natural hard drive, encoding vast amounts of information in their quantum structure. Black holes might also serve as tools for gravitational computing or as mechanisms for generating highly unusual states of matter through their extreme gravitational gradients. Some theorists have even proposed using connected black holes, wormholes, as potential mechanisms for faster-than-light information transfer or travel, though the practical and theoretical challenges of creating and stabilizing such structures remain formidable. While such technological uses remain speculative, they highlight the possibility that black holes could transition from objects of fear and mystery to essential infrastructure for life in the far-future universe. As we contemplate the formation and evolution of black holes across cosmic time, we confront not just the limits of our physical theories, but also the boundaries of our imagination. These objects, where matter is crushed beyond recognition and time itself behaves strangely, remind us that the universe is more extraordinary than our everyday experiences suggest. They represent both endings and beginnings, the deaths of massive stars, and the birth of objects that will outlast almost everything else in existence. And as we'll explore next, even these seeming eternities have their limits. For in the unimaginably distant future, black holes themselves will face a slow demise through Hawking radiation, marking perhaps the final chapter in the story of structured matter in our universe. For most of human history, black holes were considered the ultimate cosmic endings, objects so extreme that nothing, once captured, could ever escape their gravitational grip. Their very name suggested finality, collapsed stars, gravitational singularities, space-time dead ends. In classical physics, a black hole's event horizon marked an absolute boundary, a one-way membrane through which matter and energy could pass into oblivion but never return. This understanding painted black holes as eternal objects, growing steadily as they consumed matter, but never diminishing, seemingly destined to outlast everything else in the universe. This view was shattered in 1974 by a young theoretical physicist named Stephen Hawking. In a paper that would revolutionize our understanding of black holes, Hawking combined quantum field theory with general relativity to show that black holes are not truly black. Through a subtle quantum mechanical process occurring at the event horizon, black holes emit radiation, slowly losing mass and energy in the process. This emission, now known as Hawking radiation, implies that black holes are not eternal, but actually have finite lifetimes, albeit unfathomably long ones by human standards. Given enough time, measured in incomprehensibly large numbers, every black hole in the universe will eventually evaporate completely, returning their captured energy to the cosmos in a final burst of radiation. To understand Hawking radiation, we must venture into the strange realm where quantum mechanics meets gravitational physics. In quantum field theory, the vacuum of space is not truly empty, but seethes with energy, constantly producing virtual particle-antiparticle pairs that briefly pop into existence before reuniting and annihilating each other. Normally, these virtual particles have no observable effects because they exist for such short times, governed by Heisenberg's uncertainty principle. However, Hawking realized that near a black hole's event horizon, something remarkable happens to these ephemeral particles. If a virtual particle pair is created just outside the event horizon, one member of the pair can fall into the black hole, while the other escapes to infinity. The infalling particle, which must have negative energy relative to infinity to conserve various physical quantities, reduces the black hole's mass, while the escaping particle becomes real and carries away positive energy. To an outside observer, the black hole appears to emit radiation, even though the black hole itself has not allowed anything to escape from behind its event horizon. The spectrum of this radiation is almost exactly that of a perfect black body, an idealized physical object that absorbs all electromagnetic radiation, with a temperature inversely proportional to the black hole's mass. For a typical stellar black hole of about 10 solar masses, this temperature is incredibly low, approximately 1/10,000,000th of a degree above absolute zero. Supermassive black holes are even colder. Sagittarius A star, the 4 million solar mass black hole at the center of our galaxy, has a temperature of about 1/10,000,000,000th of a degree above absolute zero. This radiation is far too faint to be detected with current technology, which is why Hawking radiation remains a theoretical prediction rather than an observed phenomenon. Despite its extremely low temperature, Hawking radiation causes black holes to lose mass over time. Energy and mass are equivalent through Einstein's famous equation E = mc2, so the energy carried away by Hawking radiation comes at the expense of the black hole's mass. As a black hole loses mass, its temperature increases and the rate of radiation accelerates, creating a runaway process that eventually leads to the black hole's complete evaporation. The timescales for this evaporation are staggering. A black hole with the mass of our Sun would take approximately 10 to the power of 67 years to evaporate completely, a period about 10 to the power of 57 times longer than the current age of the universe. For the supermassive black hole at the center of our galaxy, the evaporation time extends to roughly 10 to the power of 87 years. These timescales are so vast that they dwarf not just human history, but the entire future timeline of stars, galaxies, and conventional matter. To put this in perspective, if the lifetime of a typical star like our Sun were compressed to 1 second, the evaporation time of a stellar mass black hole would still be trillions of times longer than the current age of the universe. Remarkably, smaller black holes evaporate faster than larger ones. A black hole with the mass of Mount Everest, about 10 to the power of 14 kilograms, would evaporate in approximately 10 to the power of 36 years. Still an immense period, but considerably shorter than stellar black holes. Truly microscopic black holes, if they exist, would evaporate even more quickly. A black hole with the mass of a typical car would shine with the brightness of a 1,000,000 megaton hydrogen bomb and disappear completely in a fraction of a second. Such microscopic black holes might have formed in the extreme conditions of the early universe just after the Big Bang. These primordial black holes have been proposed as potential candidates for dark matter, though observational constraints make this unlikely for most mass ranges. If they do exist, the smallest primordial black holes would have already evaporated, while larger ones could still be present, but would be extremely difficult to detect due to their small size and faint emissions. As a black hole approaches the final stages of evaporation, its behavior changes dramatically. When the black hole's mass diminishes to about 10 to the power of 11 kilograms, roughly the mass of a large mountain, its temperature reaches trillions of degrees, and it emits primarily gamma rays and high-energy particles rather than the lower-energy radiation characteristic of larger black holes. In the final second of its life, a dying black hole would release energy equivalent to billions of hydrogen bombs through a final burst of high-energy radiation. The eventual evaporation of all black holes represents one of the final chapters in the story of structured matter in our universe. After the last stars have burned out, after the last atoms have decayed, after the last planets have been swallowed by black holes or ejected into intergalactic space, black holes will be among the final structured objects remaining. Their gradual evaporation through Hawking radiation will return the captured mass energy back to the universe, albeit in a maximally disorganized form. The ultimate fate of a universe filled with evaporating black holes connects to broader questions about cosmic evolution and the thermodynamic heat death scenario. The second law of thermodynamics states that the total entropy, roughly speaking the disorder, of an isolated system never decreases over time. The emission of Hawking radiation dramatically increases entropy, transforming the relatively low entropy configuration of a black hole into a much higher entropy bath of thermal radiation. This transformation aligns with the universe's general trend toward higher entropy states. The early universe began in an extraordinarily low entropy state, with matter and energy distributed remarkably uniformly, but with small fluctuations that allowed structure formation. Over cosmic time, gravity amplified these fluctuations into stars, galaxies, and black holes, with each step in cosmic evolution increasing the total entropy. The evaporation of black holes represents one of the final steps in this entropic evolution. Yet even as black holes evaporate, certain conservation laws must be respected. Black holes can carry 3 fundamental properties: mass, or equivalently energy, angular momentum, spin, and electric charge. As a black hole evaporates, it must shed not just energy, but also any angular momentum and charge it possesses. The details of how rotating or charged black holes evaporate are more complex than for simple Schwarzschild, non-rotating, uncharged black holes. But the end result is the same: complete evaporation, with all properties ultimately converted to radiation. The conservation of information, however, presents a more profound challenge. Quantum mechanics suggests that information cannot be truly destroyed, only transformed. Yet a black hole seems to destroy information about anything that falls into it, remembering only the object's mass, charge, and angular momentum, but nothing about its detailed structure or composition. When the black hole later evaporates, the emitted Hawking radiation appears to be purely thermal, carrying no information about what fell in. This apparent conflict, known as the black hole information paradox, has troubled physicists for decades and remains an active area of research. Recent theoretical work suggests that subtle quantum correlations in Hawking radiation might encode all the information about matter that fell into the black hole, preserving information in an extraordinarily scrambled form. If true, this would mean that the final burst of radiation from a dying black hole contains, in principle, information about everything the black hole ever consumed during its existence, a cosmic memorial of sorts, preserving traces of stars, planets, and perhaps even civilizations long after they have physically ceased to exist. Regardless of how the information paradox is ultimately resolved, the evaporation of black holes through Hawking radiation marks a definitive endpoint for these objects. No matter how massive a black hole becomes by consuming matter or merging with other black holes, given enough time, it will eventually return all of its mass energy to the universe. The only exception would be if a black hole continued to absorb matter at least as quickly as it radiates energy. But in an expanding universe where matter becomes increasingly dilute, this scenario cannot continue indefinitely. Eventually, every black hole will find itself in effectively empty space, with no new matter to consume, radiating away its mass until nothing remains. The timescales involved in black hole evaporation provide a humbling perspective on cosmic history. 8 billion-year history of our universe compressed to a single day, with the Big Bang at midnight and the present moment at the next midnight. Then the time required for a stellar mass black hole to evaporate would extend tens of trillions of times longer than this cosmic day. If the current age of the universe were represented by a single grain of sand, the lifetime of a stellar mass black hole would form a pile of sand larger than the observable universe. These incomprehensible timescales remind us that the universe's future extends far beyond its past. We live in what might be considered the cosmic morning, with most of the universe's history, including the era of black hole dominance and their eventual evaporation, still ahead. The stars we see in the night sky represent just the first generation of countless stellar births and deaths that will unfold across cosmic time. Similarly, the black holes we have detected through their gravitational effects or accretion signatures represent just the beginning of black hole evolution in our universe. What will the universe look like during these distant epochs? As stars exhaust their fuel and cease to shine, galaxies will gradually darken. The expanding universe will stretch the distances between galaxy clusters beyond the cosmic horizon, making them invisible to each other. Within each bound cluster of galaxies, stars will either burn out to become white dwarfs, neutron stars, and black holes, or be ejected through gravitational interactions to wander the intergalactic void. Over time, even white dwarfs and neutron stars will decay or be captured by black holes. Eventually, each galaxy cluster will be reduced to a collection of increasingly isolated black holes, surrounded by diffuse gas, too sparse to form new stars. At this stage, black holes become the dominant structured objects in the universe. They will occasionally capture passing matter or even merge with other black holes. But these events will become increasingly rare as the universe continues to expand and matter becomes more diffuse. For the most part, these black holes will exist in solitude, slowly radiating away their mass through Hawking radiation, with the smallest evaporating first and the largest persisting the longest. The radiation produced by evaporating black holes will itself be subject to the universe's expansion. As space stretches, the wavelengths of photons and other particles elongate, reducing their energy through cosmological redshift. This means that even the final bursts of radiation from evaporating black holes will eventually be stretched into obscurity, their energy diluted across ever-expanding space. If the current acceleration of cosmic expansion continues, driven by the mysterious dark energy that comprises about 68% of the universe's energy content, then the final state of our universe may be a nearly perfect vacuum. In this scenario, even the products of black hole evaporation will be diluted to insignificance, leaving a universe that is effectively empty, cold, and dark. a state physicists call the heat death of the universe, where no further thermodynamic work is possible because everything has reached the same temperature. However, this bleak scenario is not the only possibility. Several alternative cosmic futures have been proposed based on different understandings of dark energy's nature. If dark energy is not constant but changes over time, the universe's expansion could eventually slow or even reverse, leading to a big crunch, where everything collapses back to a singularity similar to the Big Bang. In this scenario, black holes would not have time to completely evaporate before being incorporated into the final universal collapse. Other speculative scenarios include the possibility of spontaneous nucleation of new universes through quantum tunneling processes, or the emergence of complex structures through random quantum fluctuations over unfathomably long timescales, so-called Boltzmann brains, or other forms of ordered complexity arising from disorder. These possibilities, while consistent with some interpretations of quantum mechanics, remain highly speculative and push the boundaries of our current understanding of physics. For black holes specifically, the question of whether they truly evaporate completely or leave some kind of remnant remains open. Some theoretical approaches to quantum gravity suggest that the final stages of black hole evaporation may deviate from Hawking's original calculation, potentially leaving behind a stable remnant with Planck mass, about 22 micrograms, or even allowing the singularity to become exposed as a naked singularity, though the latter possibility is generally considered unlikely due to the cosmic censorship hypothesis. If stable Planck mass remnants do exist, they would constitute a form of matter unlike anything else in the universe, objects containing the information of much larger systems compressed into minute volumes, potentially persisting eternally even as the rest of the universe approaches heat death. Such objects would be incredibly difficult to detect due to their tiny size and mass, but could in principle serve as repositories of information from earlier cosmic epochs. The physics governing black hole evaporation connects to some of the most profound open questions in theoretical physics, particularly the quest for a quantum theory of gravity that reconciles general relativity with quantum mechanics. Current approaches, including string theory, loop quantum gravity, and other frameworks, offer different perspectives on the final fate of black holes. The eventual resolution of these questions may radically alter our understanding of black holes, space-time, and the ultimate destiny of our universe. For now, we can say with reasonable confidence that black holes are not eternal, but are subject to a slow decay through Hawking radiation. This process, while undetectably slow for astronomical black holes under current conditions, will eventually return their mass energy to the universe in the form of radiation. The evaporation of the last black holes would mark the end of structured matter as we understand it, leaving behind only dilute radiation in an otherwise empty cosmos, unless some deeper principle of physics intervenes to write a different ending to this cosmic story. As we contemplate the eventual death of black holes through Hawking radiation, we connect to broader questions about the ultimate fate of our universe. The timescales involved, spanning from the present to 10 to the power of 100 years in the future and beyond, stretch the limits of human imagination and scientific extrapolation. Yet, through mathematics and physical principles, we can project the evolution of our universe far beyond the lifetime of our species, our planet, our star, and even the familiar structures of galaxies and black holes. This ability to comprehend cosmic timescales, extending trillions upon trillions of years into the future, represents one of the most remarkable achievements of the human mind. Though we are ephemeral beings, living for mere decades on a planet that has existed for billions of years, our understanding reaches toward eternity. Through science, we transcend our temporal limitations, glimpsing the grand narrative of cosmic evolution from its fiery beginning to its cold, distant end. The evaporation of black holes, occurring in the unimaginably distant future, connects to our next topic, the fate of the expanding universe itself. As black holes slowly surrender their mass energy back to the cosmos through Hawking radiation, what will become of the universe as a whole? Will it continue expanding forever, or might it eventually collapse back upon itself? These questions lead us to consider the ultimate cosmic future, shaped by the mysterious dark energy that currently accelerates the universe's expansion, and by physical laws that may operate on timescales far beyond human experience. Our universe began approximately 13.8 billion years ago in the cosmic event we call the Big Bang. Not an explosion in space, but the rapid expansion of space itself from a state of extreme density and temperature. Since that moment, the universe has been expanding, its galaxies moving progressively farther apart as the cosmic web stretches. For most of the 20th century, astronomers debated whether this expansion would continue forever or eventually reverse, leading to a big crunch where all matter reconverges into a final singularity. The answer to this question, the ultimate fate of our universe, was thought to depend primarily on the total mass and energy content of the cosmos, with a denser universe eventually recollapsing and a less dense one expanding eternally. In 1998, this picture changed dramatically when two independent research teams studying distant supernovae made an astonishing discovery. The expansion of the universe is not slowing down as expected, but is actually accelerating. This acceleration implies the existence of a mysterious repulsive force working against gravity on the largest scales, a force we now call dark energy. This revelation fundamentally altered our understanding of cosmic destiny and set the stage for the most likely fate of our universe, eternal expansion, leading to a cold, dark, and increasingly empty cosmos. The precise details of this expansion, and whether it might hold surprising twists in the far future, remain among the most profound questions in modern cosmology. To understand the fate of our expanding universe, we must first appreciate the nature of this expansion. Unlike conventional explosions, where objects fly apart through space, cosmic expansion involves the stretching of space-time itself. Galaxies are not simply moving away from each other through static space. Rather, the space between them is literally expanding. Astronomers often use the analogy of a balloon with dots drawn on its surface. As the balloon inflates, all dots move away from each other, with more distant dots receding faster, not because they're moving across the balloon's surface, but because the surface itself is stretching. This expansion is quantified by Hubble's law, which states that galaxies move away from us at speeds proportional to their distance, 26 million light-years. 26 million light-years away recedes at about 70 kilometers per second, while one twice as distant recedes twice as fast. At sufficiently large distances, galaxies recede faster than the speed of light, not violating Einstein's relativity because they aren't moving through space at that speed. Rather, the intervening space itself expands at that effective rate. For decades, astronomers expected this expansion to gradually slow due to the gravitational attraction of all matter in the universe. Even if the universe lacked sufficient mass for a full recollapse, the expansion would at least decelerate over time as gravity worked against it. The discovery of accelerating expansion revealed that another force, dark energy, overwhelms gravity's influence on the largest scales, pushing galaxies apart at an ever-increasing rate. The nature of dark energy remains one of the greatest mysteries in physics. The leading hypothesis identifies it with the cosmological constant, a property of space itself first proposed by Einstein, who later rejected it, that causes space to have an intrinsic tendency to expand. In this model, each cubic meter of empty space contains a small but fixed amount of dark energy. As the universe expands, creating more empty space, the total amount of dark energy increases, accelerating the expansion in a self-reinforcing cycle. Other models propose more dynamic forms of dark energy that might change over time, perhaps eventually weakening or even reversing its repulsive effect. These theories are collectively known as quintessence models. Most observations currently favor the simpler cosmological constant interpretation, but the ultimate nature of dark energy remains uncertain, with profound implications for the universe's future. Based on current measurements, dark energy comprises about 68% of the universe's total energy content, with dark matter contributing another 27%, and ordinary visible matter, the stuff of stars, planets, and living organisms, making up less than 5%. This distribution means that dark energy now dominates the cosmic evolution, overcoming the gravitational effects of both visible and dark matter on the largest scales. The accelerating expansion driven by dark energy leads to a specific scenario for the universe's future often called the Big Freeze or heat death. In this vision, galaxies outside our local group will recede from us at increasingly rapid rates, eventually moving beyond our cosmic horizon, the maximum distance from which light can ever reach us. Once a galaxy crosses this horizon, no signal from it can ever reach us again, effectively removing it from our observable universe. This process has already begun. Of the roughly 2 trillion galaxies estimated to exist in the currently observable universe, many are already receding so rapidly that light they emit today will never reach us. As cosmic expansion accelerates, more galaxies will cross this observational threshold, gradually shrinking the number visible to any hypothetical future astronomers in our local group. Within about 100 billion years, less than 10 times the current age of the universe, all galaxies outside our local group will have vanished beyond the cosmic horizon. The night sky for any observers in that distant era would contain only the merged remnants of the Milky Way, Andromeda, and the other few dozen galaxies that comprise our gravitationally bound local group. The distant universe, with its billions of galaxies and trillions of stars, would be not just invisible, but fundamentally unreachable. Regions of space so remote that no physical interaction with them would ever be possible again. Interestingly, hypothetical civilizations arising in that far future would have no direct observational evidence for the Big Bang, cosmic expansion, or the vast universe beyond their local galaxy cluster. The cosmic microwave background, the afterglow of the Big Bang that currently provides crucial evidence for our cosmological model, would be redshifted to such long wavelengths by the expanding universe that it would become undetectable. Most of the empirical foundations of our current cosmological understanding would be erased by the very process of expansion we now study. While galaxies outside our local group will eventually become unreachable, the local group itself will remain gravitationally bound, with the Milky Way and Andromeda galaxies merging as previously discussed. Over hundreds of billions of years, the smaller galaxies in our local group will also merge into this combined structure, eventually forming a single giant elliptical galaxy, sometimes called Milkomeda, that contains all the stars and other matter from our currently separate galaxies. Within this merged galaxy, star formation will gradually cease as the available gas is either converted to stars or expelled from the galaxy by stellar processes. The last stars will form roughly 100 trillion years from now, after which no new stellar bodies will be born. The existing stars will gradually exhaust their fuel and dim, with the smaller red dwarfs persisting the longest, up to 10 trillion years for the least massive examples. As stars complete their life cycles, they will leave behind stellar remnants, white dwarfs, neutron stars, and black holes that will populate the merged galaxy. Over extremely long timescales, even these remnants will undergo significant evolution. White dwarfs will cool from their initial temperatures of tens of thousands of degrees to just a few degrees above absolute zero, becoming black dwarfs. Neutron stars will cool similarly, eventually becoming cold, dense spheres detectable only by their gravitational influence. Through processes of dynamical friction and gravitational interaction, many of these stellar remnants will spiral toward the galactic center, where they may be consumed by the supermassive black hole formed from the merger of the original galaxy's central black holes. Others will be ejected from the galaxy through close gravitational encounters, destined to wander the expanding void between galaxy clusters. Over timescales of 10 to the power of 20 years, 100 quintillion years, most remaining objects will either have been ejected from the galaxy or captured by the central supermassive black hole. The galaxy itself will darken as stars die out, with only occasional brief flashes of light from rare events like white dwarf mergers or matter falling into black holes breaking the increasing darkness. During these vast timescales, matter itself will begin to change. Protons, the building blocks of atomic nuclei, may be unstable over extremely long periods. While no proton decay has been observed during experiments spanning decades, theoretical considerations suggest that protons might decay with half-lives of at least 10 to the power of 34 years, 10 decillion years. If this occurs, all ordinary matter will gradually dissolve as its constituent protons decay into lighter particles and radiation. Even if protons are perfectly stable, quantum tunneling effects operating over unimaginably long timescales could cause matter to reconfigure in surprising ways. Quantum mechanics allows for extremely improbable events to occur given sufficient time, including the spontaneous fusion of particles or the tunneling of matter through seemingly impenetrable barriers. Over periods exceeding 10 to the power of 65 years, such quantum effects might cause all matter, even black dwarfs and neutron stars, to either collapse into black holes or disperse into elementary particles. Black holes, as we've discussed, will themselves evaporate through Hawking radiation, with the process accelerating as they lose mass. The largest supermassive black holes will persist the longest, up to 10 to the power of 100 years, but eventually even these will vanish, leaving behind only their radiated energy, now stretched to extreme wavelengths by the continuing cosmic expansion. If dark energy maintains its current properties, the ultimate fate of our universe appears to be a state of heat death, a cold, dark, nearly empty cosmos, where all matter has decayed or formed black holes that subsequently evaporated, and all remaining energy has been diluted by expansion to a nearly uniform, extremely low-density state. In this scenario, the universe approaches a state of maximum entropy, where no significant energy gradients exist to drive complex processes. The laws of thermodynamics would prevent any further large-scale structured activity, essentially bringing cosmic evolution to a halt. However, this bleak scenario isn't necessarily the final word on our cosmic fate. Several alternative possibilities arise from different theoretical understandings of dark energy's nature. If dark energy is not constant but changes over time, the universe's expansion could follow dramatically different trajectories. One alternative is the Big Rip scenario, where dark energy strengthens over time. In this model, the accelerating expansion eventually becomes so violent that it overcomes not just the gravitational bonds between galaxies, but progressively smaller structures, tearing apart galaxy clusters, then individual galaxies, then solar systems, and ultimately atoms and subatomic particles themselves. The universe would end in a finite time, with all structure destroyed by the overwhelming expansive force. The opposite possibility is that dark energy might weaken or even reverse its effect, allowing gravity to gradually reassert dominance over cosmic evolution. This could lead to a big crunch, where the currently expanding universe eventually halts its expansion and begins to contract. All matter would ultimately reconverge in a state of extreme density and temperature, perhaps similar to the Big Bang that began our cosmic story. Some theoretical models combine these scenarios, suggesting that a contracting universe might bounce at its moment of maximum compression, spawning a new expansion phase. This Big Bounce concept envisions a cyclical universe undergoing alternating periods of expansion and contraction, potentially extending infinitely into both the past and future. While appealing in its symmetry, such models face significant theoretical challenges, particularly regarding how entropy would behave across bounce events. Even more exotic possibilities emerge from quantum cosmology and string theory. Some models propose that our observable universe exists as one bubble in a much larger multiverse, with different regions exhibiting different physical laws and cosmological constants. In certain versions of these theories, new bubble universes can spontaneously nucleate within expanding space through quantum processes, creating baby universes that expand into their own separate spacetimes. Another speculative scenario involves a process called vacuum decay. Our current understanding of particle physics suggests that the universe might not be in its lowest possible energy state, essentially meaning that our physical vacuum may be metastable rather than truly stable. If this is correct, a quantum tunneling event could trigger a transition to a lower energy vacuum state, which would propagate outward at the speed of light, dramatically altering the fundamental constants of physics in the affected regions. Such an event would effectively end the universe as we know it, replacing it with a new reality governed by different physical laws. From our current scientific understanding, the heat death scenario driven by persistent dark energy remains the most likely ultimate fate for our universe. However, the true nature of dark energy, and thus the universe's ultimate destiny, remains one of the greatest unresolved questions in physics. Ongoing and future astronomical observations, laboratory experiments, and theoretical developments may yet reveal surprises that rewrite our understanding of cosmic fate. What's particularly striking about these various scenarios is their timescales, extending so far beyond human experience that they challenge our ability to comprehend. Even the shortest timescale discussed, the roughly 100 billion years until all external galaxies vanish beyond our cosmic horizon, spans more than 7 times the current age of the universe. The later stages, involving proton decay, quantum tunneling, and black hole evaporation, unfold over periods so vast that they exceed the current age of the universe by factors of trillions, quadrillions, or even greater magnitudes. These incomprehensible timescales highlight an important truth about cosmic evolution. We live in the universe's youth. 8 billion years old, our universe has only begun its journey. The era of stars and galaxies, the cosmic period that allows for complex chemistry, planets, and life, represents just the opening chapter in a story that will continue for trillions upon trillions of years. The universe's past is brief compared to its future. This realization raises profound questions about the potential for life in these distant future eras. While biological life as we know it depends on energy flows from stars, could other forms of complexity arise in the far future universe? Could advanced civilizations find ways to survive the darkening cosmos, perhaps by harvesting energy from rotating black holes, or tapping the residual heat differentials that would persist even in an aging universe? Theoretical physicist Freeman Dyson was among the first to seriously consider these questions, proposing that intelligent beings might adapt to the cooling universe by operating at increasingly lower temperatures, extending their subjective lifetimes even as objective time accelerates. Other researchers have suggested that advanced civilizations might migrate to the vicinity of black holes, where gravitational time dilation would allow them to experience less of the universe's aging, effectively watching cosmic evolution in fast forward from their relatively slow time reference frame. More speculatively, if consciousness or intelligence could somehow be transferred to formats that don't depend on conventional matter, perhaps existing as patterns in radiation fields or other exotic substrates, life might persist even after ordinary matter has decayed. Such existence would be unimaginably different from biological life, perhaps beyond our ability to recognize or comprehend. Regardless of whether life can adapt to these distant future conditions, the accelerating cosmic expansion shapes the ultimate boundaries of causality and knowledge. As galaxies recede beyond our cosmic horizon, regions of the universe become permanently disconnected from one another. No light, information, or influence of any kind can pass between these separated regions. The observable universe for any given observer gradually shrinks in comoving terms, imposing fundamental limits on what can ever be known or affected from any particular location. This causal disconnection raises philosophical questions about the meaning of existence for regions that can never again interact. If two parts of the universe can never exchange information or influence each other in any way, in what sense are they part of the same reality? These questions connect cosmology to deep philosophical inquiries about the nature of existence, knowledge, and reality itself. As we contemplate these distant futures, we're reminded that the universe we observe today, filled with galaxies, stars, and the potential for life, exists within a privileged cosmic epoch. We live in what cosmologists call the stelliferous era, when stars actively form and shine, providing energy for complex chemical processes and potential life. This era began a few 100 million years after the Big Bang, when the first stars ignited, and will continue for roughly 100 trillion years until the last stars burn out. After the stelliferous era comes the degenerate era, lasting from approximately 10 to the power of 14 to 10 to the power of 40 years, when stellar remnants like white dwarfs, neutron stars, and black holes dominate the universe. Following this is the black hole era, from roughly 10 to the power of 40 to 10 to the power of 100 years, when black holes become the only significant structured objects remaining. Finally, after all black holes evaporate, the universe enters the dark era, extending from 10 to the power of 100 years into the infinite future, characterized by an increasingly diffuse sea of elementary particles, photons, and neutrinos, with no large-scale structure or organized complexity. Our existence in the stelliferous era allows us to observe and understand cosmic history in ways that would be impossible for any hypothetical entities arising in later epochs. The evidence for the Big Bang, Cosmic expansion and the formation of structure through gravitational attraction remains visible to us through telescopic observations. Future observers, after galaxies have vanished beyond the cosmic horizon and the cosmic microwave background has redshifted into undetectability, would have no observational access to these fundamental aspects of cosmic history. In this sense, we are fortunate observers, blessed with a cosmic perspective that reveals both the universe's origins and its likely fate. Through science, we've pieced together a cosmic narrative spanning from the first moments after the Big Bang to the unimaginably distant future when the last black holes evaporate into radiation. This narrative connects us to timescales far beyond human experience, linking our brief existence to the grand arc of cosmic evolution. As the universe expands and galaxies recede beyond our vision, as stars exhaust their fuel and slowly fade, as matter itself gradually decays or collapses into black holes that eventually evaporate, the cosmos transitions from its current state of dynamic activity to increasing quiescence. Yet even in this seemingly bleak scenario, the fundamental laws of physics that govern these processes remain a source of wonder. The same principles that allow us to understand stellar fusion, black hole evaporation, and cosmic expansion connect us intellectually to these distant futures, allowing us to comprehend cosmic destinies we will never witness. The fate of our expanding universe, with its progression toward increasingly sparse, cold, and simple states, leads naturally to questions about the significance of the complex structures, including life and consciousness, that have emerged during the universe's youth. If the cosmos ultimately trends toward simplicity and dissolution, what meaning can we attribute to the temporary complexity that arises along the way? This question connects cosmology to philosophy, inviting us to consider the significance of our moment in cosmic history. Yet even as the expanding universe progresses towards states of increasing entropy and simplicity, questions remain about what other transformations might occur in these distant epochs. As we turn our attention to the universe's darkening future, when the last stars have faded and galaxies have disappeared beyond the cosmic horizon, we confront the question of what existence means in a cosmos dominated by increasingly isolated and long-lived stellar remnants. It is to these final dying embers of the once bright cosmos that we now turn our attention. From our vantage point in the present cosmos, stars dominate the visible universe. These luminous spheres of plasma, from the brilliant blue-white giants that outshine millions of suns to the dim red dwarfs barely able to sustain fusion, collectively form the galaxies we observe across the cosmic expanse. They create the heavy elements essential for planets and life, warm their orbiting worlds, and provide the energy gradients that ultimately power complex chemistry and biology. Stars are so fundamental to our conception of the cosmos that a universe without them seems almost unimaginable. Yet this starless state represents the inevitable future toward which our universe trends. As the accelerating expansion isolates galaxy clusters and the finite supply of gas is gradually converted to stars or expelled into intergalactic space, star formation will slowly cease. The existing stars will burn through their nuclear fuel, one by one extinguishing their fires, until the universe transitions from its current luminous state to perpetual darkness, a cosmic night that once fallen will never again be broken by stellar dawn. To understand the death of the last stars, we must first appreciate the extraordinary diversity of stellar lifespans. Not all stars live and die on the same timescale. Our Sun, a fairly typical yellow dwarf, will shine for about 10 billion years before exhausting its core hydrogen and beginning its transformation to a red giant. More massive stars burn through their fuel much faster. A star with 10 times the Sun's mass might exist for just 20 million years before exploding as a supernova. The most massive stars known, with over 150 solar masses, may live for a mere 2 to 3 million years, a cosmic eye blink in astronomical terms. The briefest stellar lives belong to these massive stars, which burn hot and die young. Despite their spectacular nature and crucial role in producing heavy elements, these stellar giants are cosmic sprinters, appearing and vanishing in quick succession. In the far future universe, as gas supplies dwindle and star formation declines, these massive stars will be among the first stellar types to disappear entirely. Without sufficient gas clouds to form new massive stars, the spectacular supernovae they produce will become increasingly rare cosmic events, eventually ceasing altogether perhaps 100 billion to 1 trillion years from now. The stars with the longest lifespans are the red dwarfs, the smallest, coolest, and most numerous stellar class in the universe. 5 times that of our Sun, these diminutive stars burn their hydrogen fuel so slowly and efficiently that they can shine for trillions of years. 2 light-years distance is a red dwarf expected to shine for about 4 trillion years, roughly 400 times longer than our Sun's entire lifespan. The smallest red dwarfs, just massive enough to sustain fusion, might continue shining for up to 10 trillion years. Unlike our Sun and other more massive stars, red dwarfs burn through their hydrogen in a unique way. Rather than maintaining separate core and envelope regions, convection currents in these small stars ensure that all hydrogen throughout the star eventually becomes available for fusion. This allows them to convert nearly all their hydrogen to helium, much more efficient than larger stars like our Sun, which will exhaust only its core hydrogen before entering the red giant phase. Red dwarfs are also fully convective, meaning their internal material constantly mixes, bringing fresh hydrogen to the core and distributing heat throughout the star. Due to these efficient fusion processes and low masses, red dwarfs never expand into red giants. They gradually increase in luminosity as they age, eventually burning all available hydrogen and slowly cooling into white dwarfs without experiencing the dramatic expansion and contraction phases that characterize the deaths of larger stars. The transition from red dwarf to white dwarf is so gradual that astronomers sometimes call these ancient, nearing exhaustion stars blue dwarfs, reflecting their slightly higher surface temperatures as they compress and prepare for their final cooling phase. As the universe ages and star formation ceases, the stellar population will steadily shift toward these long-lived red dwarfs. In our present universe, massive short-lived stars continually form and die, replenished by ongoing star formation in gas-rich regions. Once star formation ends, this replenishment stops. The bright, massive stars will disappear first, followed by intermediate stars like our Sun, leaving only the red dwarfs to illuminate the aging cosmos. Within about 100 trillion years, less than 10 times the lifespan of the smallest red dwarfs, even these stellar survivors will begin to fade, having exhausted their nuclear fuel. Interestingly, another class of stars may briefly outshine these ancient red dwarfs in the late stages of the stelliferous era. Binary star systems containing white dwarfs can produce spectacular thermonuclear explosions when the white dwarf accretes matter from its companion. These events, called type Ia supernovae, can briefly outshine entire galaxies. As stars age and populate the universe with more white dwarfs, these explosive events may become the brightest stellar phenomena in the aging cosmos, providing brief flashes of light in the increasingly dark universe before they too fade away as suitable binary systems become rarer. The transition from the stelliferous era, dominated by shining stars, to the degenerate era, dominated by stellar remnants, will occur gradually over these vast timescales. As red dwarfs exhaust their fuel over trillions of years, they will cool to become white dwarfs, dense, Earth-sized objects consisting primarily of carbon and oxygen, no longer generating energy through fusion, but still glowing from residual heat. Initially, these white dwarfs shine with surface temperatures of around 100,000 degrees Celsius, appearing blue-white. Over time, they gradually cool and dim, their color shifting through the spectrum from white to yellow, then to red, and eventually becoming too cool to emit visible light at all. The cooling process for white dwarfs extends over extraordinary timescales. A typical white dwarf might take 10 billion years to cool from its initial temperature to about 5,000 degrees Celsius, comparable to our Sun's current surface temperature. Another 100 billion years might pass before it cools to 1,500 degrees Celsius, glowing a dull red. Eventually, after trillions of years, the white dwarf's temperature will approach that of the cosmic background, rendering it virtually invisible, a black dwarf, radiating only the faintest infrared glow. These black dwarfs represent the final fate of most stars in our universe, including our Sun. Unlike their still hot white dwarf precursors, black dwarfs no longer emit significant electromagnetic radiation and are essentially dead stars, dense spheres of carbon and oxygen with masses comparable to our Sun, but compressed to the size of Earth, drifting through the cosmic darkness. Though no black dwarfs exist yet in our universe, which is too young for any white dwarf to have cooled completely, they will ultimately become the most common stellar objects in the far future cosmos. Other stellar remnants will share the universe with these black dwarfs. Neutron stars, the ultra-dense remains of moderately massive stars that exploded as supernovae, also gradually cool over time. Currently, young neutron stars have surface temperatures of several million degrees Celsius, making them visible primarily as sources of X-rays. Like white dwarfs, they will cool over trillions of years, eventually becoming cold neutron degenerate objects detectable only by their gravitational effects or through rare energetic events like collisions. The stellar remnant population will also include black holes of various sizes, from stellar mass objects a few times heavier than our Sun, to supermassive black holes billions of times more massive. While these objects do not shine in the conventional sense, they can generate observable radiation when they accrete matter from their surroundings. In the distant future, as matter becomes increasingly scarce, these accretion events will become rare, leaving black holes as essentially invisible objects, detectable only through their gravitational influence on passing bodies, or eventually through the faint Hawking radiation they emit. As the last red dwarfs fade and stellar remnants cool into invisibility, the universe will grow increasingly dark. By about 100 trillion years from now, a period 7,000 times longer than the current age of the universe, even the longest-lived stars will have exhausted their fusion fuel. The only brief flashes of light might come from rare catastrophic events like collision or mergers of stellar remnants, or the final death spirals of binary systems. These momentary bursts would briefly illuminate their local regions before fading away, leaving the cosmos in darkness once again. This transition to darkness will dramatically change the character of the universe. Currently, stars provide the energy that drives most astronomical phenomena and enables the complex chemistry necessary for life. Their light allows astronomers to observe and study distant objects, mapping the structure and history of the cosmos. Without starlight, the universe becomes essentially invisible in conventional terms, with vast distances of utterly black space separating the cooling remnants of once bright galaxies. What would the night sky look like during these transitional eras? For hypothetical observers existing 100 billion years from now, when most stars like our Sun have already died but red dwarfs still shine, the sky would appear dramatically different from our current view. The Milky Way's familiar band would be transformed into a dimmer, redder swath dominated by low-mass stars. Most familiar constellations would be unrecognizable, as the bright blue and white stars that form many of their key points would have long since evolved into stellar remnants. By 1 trillion years from now, with star formation having ceased and only the smallest red dwarfs still shining, the night sky would be dramatically darker than today's, with perhaps just a few hundred visible stars rather than the thousands visible from a dark site today. The stars would be predominantly red, creating a night sky with a distinctly ruddy appearance. Most galaxies beyond our local group would have receded beyond the cosmic horizon, making the observable universe seem much smaller and emptier. By 100 trillion years, as even the longest-lived red dwarfs begin to fail, the night sky would grow darker still. An observer might see only a handful of dim, red stars in their entire sky, with vast darkness between them. The concept of a bright, star-filled night sky, so fundamental to human experience and culture throughout history, would become an ancient memory, recorded only in whatever historical records might have survived these unimaginable time spans. Eventually, perhaps around 10 to the power of 15 years, 1 quadrillion years from now, the last feeble light from the final dying red dwarf would flicker out. All remaining stellar objects would be stellar remnants, white dwarfs gradually cooling to become black dwarfs, cold neutron stars, and black holes. At this point, the universe enters what cosmologists call the degenerate era, characterized by these stellar corpses rather than active stars. Any light would come not from fusion reactions, but from occasional white dwarf mergers, matter falling into black holes, or the annihilation of particles and antiparticles, rare events in an increasingly empty cosmos. The darkness that falls with the death of the last star is profound, not just in its totality, but in its permanence. Unlike previous cosmic eras where darkness could be broken by the birth of new stars, this final darkness will never be lifted. The universe will lack both the concentrated gas clouds needed to form new stars and the triggering mechanisms, such as supernova shockwaves, that initiate star formation. 8 billion years ago. This eternal night will have profound implications for any hypothetical intelligence that might still exist. Life as we know it depends utterly on stellar energy, either directly through photosynthesis or indirectly through food chains, ultimately powered by sunlight. Advanced civilizations might extend their existence by moving to the vicinity of the longest-lived stars, or by developing technologies to harness energy from other sources. But the cessation of stellar fusion removes the primary energy source that has powered cosmic evolution throughout the universe's history. Theoretical physicist Freeman Dyson and others have speculated about how life might adapt to these changing conditions. As stars become scarcer and cooler, life could evolve or be engineered to function at progressively lower temperatures, possibly transitioning to exotic substrates, unlike the carbon-based biochemistry familiar to us. By operating more slowly at lower temperatures, such life forms might subjectively experience the accelerating pace of cosmic evolution as slowed, allowing them to persist through these vast timescales despite objective limits on energy availability. Other adaptation strategies might include migrating to the vicinity of white dwarfs or neutron stars to harvest their residual heat, or developing technologies to extract energy from rotating black holes through the Penrose process. More exotic possibilities include utilizing quantum vacuum fluctuations, exploiting slight temperature differentials in the cosmic background radiation, or even restructuring into forms that require minimal energy input to maintain consciousness or information processing. Regardless of whether life could adapt to these challenging conditions, the death of the last stars marks the end of the universe as a vibrant, energy-rich environment. The cosmos transitions from a dynamic system with numerous energy gradients driving complex processes to an increasingly quiescent state, trending toward thermodynamic equilibrium, what physicists call heat death, where all energy is distributed uniformly and no significant temperature differences exist to drive work or complexity. While the timescales involved in this transition stretch human comprehension, the physical principles governing the deaths of stars are well understood. Stars are, in essence, systems fighting against the inexorable pull of gravity. They maintain their structure through the outward pressure generated by nuclear fusion in their cores, converting matter to energy according to Einstein's famous E=mc2 equation. Once a star exhausts the fuel available for fusion at the temperatures and pressures it can generate, gravitational collapse becomes inevitable, leading to the formation of stellar remnants. The final black dwarfs resulting from this process represent highly ordered low-entropy states of matter, carbon and oxygen atoms arranged in crystalline lattices similar to diamonds, compressed by gravity but no longer generating energy. Over even longer timescales, quantum processes may cause further evolution of these objects. Quantum tunneling could, in theory, allow protons to overcome the repulsive electrical forces that keep atomic nuclei apart, enabling nuclear fusion even at the extremely low temperatures of black dwarfs. These processes would occur on timescales so vast, beyond 10 to the power of 1500 years, that they make the stellar era seem instantaneous by comparison. Eventually, quantum tunneling might convert much of the carbon and oxygen in black dwarfs to iron-56, the most stable isotope of any element. Such iron stars would represent a further step in the universe's journey towards states of maximum stability and minimum available energy. The death of stars also alters the universe's chemical evolution. Throughout the stelliferous era, successive generations of stars have enriched the cosmos with progressively heavier elements, creating the chemical diversity necessary for planets and life. With the end of stellar fusion and supernova explosions, this nuclear synthesis ceases. The universe's chemical composition becomes fixed, with no new heavy elements being created except through rare events like neutron star collisions. Over extraordinarily long timescales, radioactive decay will gradually convert unstable isotopes to stable ones, slightly shifting the cosmic abundance ratios, but adding no new complexity to the universe's chemistry. As we contemplate the darkening cosmos, we confront a universe transitioning from its bright, active youth to a dim, quiescent middle age, and eventually to cold, dark senescence. The death of the last stars represents a fundamental transition in cosmic history, as significant in its way as the ignition of the first stars that ended the cosmic dark ages. Yet unlike that earlier transition from darkness to light, the final darkness will not be followed by a new dawn. Once the last stellar embers fade, the universe enters a new and fundamentally different phase of its existence, a phase dominated not by the bright fusion fires that have defined the cosmos for billions of years, but by the cold, dark remnants of stars long dead. The universe that emerges after stellar extinction will be almost unrecognizable compared to the one we observe today. Without stars to provide reference points, distance scales, and illumination, the cosmos becomes an increasingly diffuse collection of stellar remnants, white dwarfs cooling to become black dwarfs, neutron stars gradually growing colder, and black holes of various sizes quietly waiting out the eons. These objects will drift through the darkness, occasionally interacting through gravitational encounters, but mostly existing in isolation, separated by distances that grow ever larger as cosmic expansion continues. This stark vision of cosmic darkness might seem bleak from our perspective, embedded as we are in a universe still bright with starlight and rich with stellar processes. Yet it represents the natural evolution of our universe according to the physical laws we have discovered. Just as individual stars follow a life cycle from birth to death, the stelliferous universe itself follows a grand arc from its luminous youth to eventual darkness. The death of stars is not a cosmic catastrophe, but the expected outcome of fundamental physical processes playing out across unimaginable timescales. As we turn our attention from the death of stars to the potential for life in this darkening cosmos, we confront questions about adaptation, survival, and meaning in a universe trending towards states of increasing entropy and simplicity. Can complexity persist without the energy provided by stars? Might life find other sources of energy and organization in the post-stellar universe? These questions connect our understanding of stellar evolution to broader considerations about the future of complexity and consciousness in the aging cosmos. As the last stars in our universe flicker and fade, a profound question emerges. Could life, in any form, persist in such a cold, dark cosmos? This isn't merely scientific speculation, but a profound inquiry into the resilience of existence itself. As we venture into the realm of the universe's deep future, we enter a landscape that challenges our very conception of life, consciousness, and possibility. The answers, or lack thereof, speak not just to the fate of hypothetical future beings, but to the meaning of our own existence in this vast cosmic drama. In the unimaginably distant future, when the last red dwarf stars exhaust their hydrogen fuel after trillions upon trillions of years, conventional biological life as we understand it would seemingly have no place. These humble red dwarfs, the most common stars in our universe, burn their fuel so slowly and efficiently that they can shine for up to 10 trillion years, over 700 times longer than our sun's total lifespan. Yet even these cosmic marathoners must eventually exhaust their nuclear fuel. Without stellar energy to drive photosynthesis or provide warmth, the biological processes we associate with living organisms would become impossible. The intricate dance of carbon-based molecules that sustains life on Earth would grind to a halt in a universe where the ambient temperature approaches absolute zero, -273.15 degrees Celsius. Yet the story of life in our universe may not end there, for the ingenuity of intelligence might transcend the limitations of biology. Advanced civilizations, should they exist for millions or billions of years, might evolve beyond their biological origins. Consider entities that upload their consciousness into quantum computers or synthetic substrates, beings whose metabolism requires vastly less energy than biological systems. While contemporary computers generate significant heat, theoretical physicists have calculated that computation itself can be extraordinarily efficient. Such post-biological intelligences might harness energy at efficiencies approaching the Landauer limit, which describes the minimum amount of energy required to erase a bit of information, approximately 3 × 10 to the -21 joules at room temperature. These entities would be almost unrecognizable to us, intelligence without bodies, thought without neurons, consciousness persisting in substrates we can barely conceptualize today. Their psychology, values, and perception of reality would likely differ so dramatically from our own that communication, should it somehow occur across the vast gulf of time, might be impossible. Yet they would be our descendants in a philosophical sense, inheritors of the cosmic torch of awareness first kindled in the early universe. These civilizations might construct massive energy-harvesting structures around the dying embers of stars, perhaps even around evaporating black holes. Black holes, once thought to be perfectly black, actually emit a faint radiation discovered by Stephen Hawking in 1974. This Hawking radiation, though incredibly feeble by our standards, could power highly efficient computational processes for time periods that dwarf the current age of the universe. A civilization might concentrate its activities into brief bursts, entering dormant states for eons between computations to conserve what little energy remains. Imagine consciousness that hibernates for billions of years, awakening only momentarily to process new information before returning to dormancy. A tempo of existence vastly different from our continuous awareness. Some theoretical physicists speculate about even more exotic possibilities. Freeman Dyson proposed that intelligent entities might slow down their subjective experience of time as energy becomes scarcer, effectively stretching their conscious existence across the emptiness of deep time. Though each thought might take millions of years to complete when measured by our standards, to such beings, consciousness would continue uninterrupted. This conceptual framework challenges our intuitive understanding of time and experience. Perhaps consciousness need not operate at the speed to which humans are accustomed. Dyson envisioned consciousness that would experience the passage of time logarithmically. As available energy decreases exponentially, subjective experience would slow at a matching rate, creating a form of temporal immortality. The physicist and mathematician Frank Tipler proposed an even more radical possibility in his omega point theory. He suggested that in the final moments of a collapsing universe, an advanced civilization might harness the infinite energy of the collapse to perform infinite computations in what would be, for external observers, a finite time. This would essentially create a computational afterlife, where simulated minds could experience subjective eternity in the universe's final moments. While most physicists consider Tipler's specific proposal speculative at best, it illustrates how the boundaries between physics, computer science, and philosophy blur when we contemplate existence at cosmic extremes. Tipler's theory depends on the universe eventually collapsing rather than expanding forever, a scenario that current observations make seem unlikely. However, the general concept of harnessing gravitational energy for computation remains valid. Rotating black holes, in particular, contain enormous reserves of potentially extractable energy in their angular momentum. A sufficiently advanced civilization might construct massive structures to tap into this energy, similar to the Penrose process described by physicist Roger Penrose in 1969. As the universe approaches its thermal equilibrium, the state where no usable energy gradients remain, even these ultra-efficient entities would face extinction. At this point, the universe enters what physicists call the heat death, where meaningful structures and organized processes become thermodynamically impossible. All matter would eventually decay. Protons would disintegrate after perhaps 10 to the power of 40 years, leaving nothing but a dilute soup of photons, neutrinos, and electrons spread across an ever-expanding void. The concept of proton decay emerges from grand unified theories in physics, which predict that protons are not truly stable but have half-lives so immense that we've never observed one decay in laboratory settings. Imagine the universe at this stage, stretched so vast that the distance between adjacent elementary particles might exceed the current observable universe. With no stars, no planets, not even atoms remaining, the cosmos would reach a state of maximum entropy. The gradient between energy states that drives all processes, from nuclear fusion in stars to the electrochemical signals in our brains, would flatten completely. The arrow of time itself might lose meaning in such a universe, as events become so rare that the concept of before and after blurs into irrelevance. Yet even here, at the apparent end of all things, quantum mechanics offers a bizarre possibility. In a universe of perfect equilibrium, random quantum fluctuations could, in principle, momentarily organize matter into complex states. These fluctuations arise from the inherent probabilistic nature of quantum physics, the same uncertainty principle that allows virtual particles to briefly pop into existence from the quantum vacuum. The most mind-bending prediction stemming from this is the concept of Boltzmann brains, fully formed conscious entities appearing spontaneously from quantum fluctuations, existing just long enough to have a few thoughts before dissolving back into the void. Named after the 19th century physicist Ludwig Boltzmann, these hypothetical entities wouldn't arise from evolution or design, but from the sheer improbability of particles randomly organizing themselves into a conscious configuration. The mathematics suggests that given enough time, and the post-stellar universe would have time in abundance, such improbable events become not just possible, but inevitable. In the quiet emptiness between evaporating black holes, consciousness might briefly flicker into existence, contemplating its own strange birth before the fluctuation dissipates and returns to chaos. The theoretical physicist Andreas Albrecht has explored this concept in depth, noting that while the probability of a Boltzmann brain forming spontaneously is inconceivably small, the timescales available in an eternal universe are even more inconceivably large. The calculation involves comparing two unfathomable quantities: the exponentially tiny probability of random particles organizing into a conscious entity versus the exponentially vast time available for such organization to occur by chance. When these calculations are performed, many cosmological models predict that Boltzmann brains would eventually outnumber conventional evolved consciousness by an overwhelming margin. This leads to a profound philosophical conundrum. In the final stages of our universe, would these brief, isolated moments of consciousness outnumber all the conscious experiences that occurred during the stelliferous era of stars and galaxies? Would the universe's predominant experience of itself ultimately be these disconnected, contextless flashes of awareness, emerging from nothing and returning to nothing? Some estimates suggest that Boltzmann brains would outnumber conventional minds by a factor of 10 to the power of 10 to the power of 50, a number so vast it defies comprehension. Some cosmologists find this conclusion so disturbing that they consider it evidence against our current understanding of physics. Surely, they argue, a universe that primarily produces disembodied minds floating in emptiness seems fundamentally absurd. This Boltzmann brain paradox continues to challenge our deepest assumptions about reality, causality, and the nature of time itself. It raises uncomfortable questions about what we mean by typical observers in the universe. If most conscious entities are Boltzmann brains, why aren't we? Why do we observe a highly ordered cosmos with consistent physical laws, rather than the chaotic perceptions we would expect from a consciousness born of random fluctuations? Physicist Sean Carroll has argued that this paradox points to a serious problem with our cosmological models. If our theories predict that most observers should be Boltzmann brains, yet we clearly are not, then something must be wrong with our theories. Carroll suggests that either the universe is not eternal in the way current models predict, or the fluctuations that could produce Boltzmann brains are somehow suppressed by quantum mechanical effects we don't yet understand. The philosopher Nick Bostrom approached this question through his simulation hypothesis, suggesting that advanced civilizations might create vast numbers of simulated universes, populating them with conscious entities. If such simulations are possible and become widespread, then statistically speaking, most conscious beings would exist within simulations rather than in base reality. This provides a potential solution to the Boltzmann brain problem. Perhaps we exist in an ordered universe precisely because our reality is a constructed one, designed to support structured consciousness rather than random fluctuations. Beyond even these strange possibilities lies the domain of speculative physics, theories that suggest our universe might not be alone. Some versions of inflationary cosmology propose that new universes continually bud off from our own, creating regions of space-time with potentially different physical laws. If true, perhaps the most advanced civilizations might find ways to send information, or even themselves, into these nascent cosmos. Imagine a civilization that exists not just to survive, but to seed new universes with the conditions necessary for life and intelligence, becoming cosmic gardeners in an endless multiverse. The physicist Alan Guth, one of the originators of inflation theory, has suggested that advanced civilizations might theoretically create baby universes in laboratory settings, essentially engineering new cosmic domains with customized physical parameters. While the energy requirements for such creation would be astronomical by current standards, they might be achievable for post-stellar civilizations that have mastered the extraction of energy from black holes or other exotic sources. These engineered universes might serve as escape hatches from our universe's inevitable heat death, allowing consciousness to transcend the limitations of our particular cosmic domain. String theory and its extension, M theory, suggest the possibility of brains, multi-dimensional structures that could harbor entire universes. Some physicists speculate that the collision of such brains might trigger new Big Bangs, creating fresh universes with their own space-time continua. Could an advanced civilization find ways to navigate or influence these higher dimensional structures, effectively transcending the death of their home universe? While such possibilities remain firmly in the realm of theoretical physics, they illustrate how the boundaries of what we consider possible continue to expand as our understanding deepens. Another possibility comes from theoretical physics and computer science. If consciousness can be understood as information processing, then sufficiently advanced civilizations might create simulated universes within their computational substrates. These basement universes could house artificial intelligences with their own internal experiences of reality. In the dying moments of our cosmos, trillions of simulated realities might flicker into existence, each experiencing its own subjective eternity in what would be mere moments of objective time. This concept of nested realities challenges our understanding of what constitutes real existence. Perhaps reality is less about physical substrate and more about information complexity and coherence. The theoretical physicist Lee Smolin proposed a fascinating concept called cosmological natural selection, suggesting that black holes might give birth to new universes with slightly modified physical laws. Over time, this would create an evolutionary pressure favoring universes that maximize black hole production. If intelligent life could somehow influence black hole formation, it might indirectly participate in this cosmic evolutionary process, shaping the properties of daughter universes. This represents another pathway through which life might transcend the confines of a single universe's lifetime. In Smolin's framework, universes that produce many black holes would have more offspring, leading to a kind of cosmic Darwinism. Interestingly, the physical constants that allow for the existence of stars, galaxies, and complex chemistry, the same constants that enable life to exist, also tend to create conditions favorable for black hole formation. This correlation might explain why our universe seems finely tuned for complexity without invoking either random chance or intelligent design. Physicist Roger Penrose proposed yet another possibility, the conformal cyclic cosmology hypothesis. In this model, after the universe reaches maximum entropy and all matter has decayed, the distinction between the infinitely large and the infinitesimally small loses meaning. The universe resets into conditions resembling those after the Big Bang, beginning a new eon. If true, the distant future of our universe may simultaneously be the birth of another. Penrose has even suggested that we might find evidence of previous cosmic cycles imprinted in the cosmic microwave background radiation, the afterglow of our own Big Bang. The speculative nature of these theories reminds us of how limited our understanding remains, despite the remarkable progress of modern physics. Our theories of quantum mechanics and general relativity, both spectacularly successful in their domains, remain fundamentally incompatible. A true theory of quantum gravity might reveal possibilities for the far future that we cannot currently imagine. Perhaps the fate of consciousness in our universe hinges on physical principles that 21st century humans have yet to discover. These speculations force us to confront fundamental questions about consciousness, purpose, and meaning. Is a universe without observers truly a universe at all? The philosopher George Berkeley famously proposed that to be is to be perceived, suggesting that existence itself might be observer-dependent. If consciousness is the universe's way of experiencing itself, would the cosmos somehow find a way to maintain awareness, even as conventional physics suggests it should fade into darkness? These questions traverse the boundaries between physics, philosophy, and metaphysics. The concept of panpsychism, the view that consciousness is fundamental to reality rather than emerging solely from complex biological systems, offers another perspective on these questions. If consciousness exists in some form at all levels of reality, perhaps it cannot be extinguished entirely, even in a universe approaching maximum entropy. While mainstream physics doesn't incorporate consciousness as a fundamental property, the enduring mystery of how subjective experience arises from physical processes keeps such philosophical alternatives on the periphery of scientific discourse. Philosopher Thomas Nagel has argued that the emergence of consciousness from purely physical processes represents an explanatory gap in our scientific understanding, what philosophers call the hard problem of consciousness. If consciousness is indeed a fundamental aspect of reality, rather than merely an emergent property of certain physical systems, then perhaps it persists in some form, even as organized matter dissipates. This perspective suggests that the universe's capacity for self-awareness might be more resilient than conventional physics would predict. For early 21st century humans, these questions may seem abstract, even irrelevant, yet they speak to our deepest yearnings, to understand not just where we came from, but where everything is ultimately headed. The transient nature of our species becomes even more apparent when we contemplate these cosmic timescales. Even if humanity were to survive for 1 million years, an extraordinary achievement, we would still witness less than a billionth of the universe's possible future. We exist in what might be called the stelliferous era, the relatively brief period when stars illuminate the cosmos and complex structures can readily form. Astronomer Fred Adams has divided the future of the universe into 5 eras: the primordial era, already past; the stelliferous era, our current epoch; the degenerate era, when stars are gone but white dwarfs and other stellar remnants remain; the black hole era, when only black holes remain; and finally the dark era, after even black holes have evaporated. Our species has emerged remarkably early in this cosmic timeline, when just about 1% of the total stars that will ever be born have appeared. We live in the cosmic equivalent of spring, when energy flows abundantly and complex structures readily form. Perhaps what makes these speculations so poignant is the contrast they create between the brevity of our moment in cosmic history and the vastness of time that will follow. We are among the universe's early inhabitants, born when stars still blaze across the heavens, when galaxies still crowd the sky, when the cosmos still pulses with available energy. Our brief window of existence coincides with what might be called the universe's most vibrant spring. The poet Percy Bysshe Shelley captured this sentiment when he wrote, "The one remains, the many change and pass. Heaven's light forever shines, earth's shadows fly." We are fleeting shadows, yet we contemplate the eternal. This perspective offers both humility and wonder. Humility in recognizing our temporal insignificance, and wonder in appreciating how fortunate we are to exist during this remarkably energetic chapter of cosmic history. We may never witness the universe's winter, but we can contemplate it, imagine it, and in doing so, expand our consciousness beyond the constraints of our biological lifespans. The cosmologist Carl Sagan once observed that we are star stuff contemplating the stars, a poetic recognition that the universe has evolved the capacity to reflect upon itself through the consciousness of living beings. The atoms in our bodies, carbon, nitrogen, oxygen, and other elements heavier than hydrogen and helium, were forged in the nuclear furnaces of ancient stars that exploded as supernovae billions of years ago. In this profound sense, we are not merely in the universe, we are of the universe. Our consciousness represents matter organized into such complex patterns that it can turn back and study its own origins. This recursive loop, the cosmos examining itself through the lens of conscious beings, may be one of the most remarkable phenomena in existence. The last possible life forms in the universe remind us that existence itself is precious, not just human existence or Earth's biosphere, but the very phenomenon of organized complexity in a universe that seems destined for simplicity. Whether consciousness persists until the final moments of our cosmos or fades long before, the question itself reflects something profound about human awareness. Our ability to project our minds across timescales that our bodies could never experience. As we ponder these distant futures, we're engaging in a uniquely human form of time travel, not physically journeying forward, but mentally extending ourselves beyond our biological horizons. In doing so, we participate in something remarkable. The universe, through us, contemplates its own mortality. We are, as the philosopher Alan Watts suggested, the universe experiencing itself as human for a little while. Perhaps the true significance of consciousness lies not in its indefinite persistence, but in the depth and richness of its momentary existence. The physicist Brian Greene captured this sentiment eloquently. We are the cosmos made conscious, and life is the means by which the universe understands itself. Even if consciousness proves to be a transient phenomenon in cosmic history, the meaning and value it creates in its brief existence may be the universe's most remarkable achievement. In the words of the philosopher Bertrand Russell, even in the vast darkness of the universe, it is the brief light of consciousness that gives meaning to existence. As we contemplate the seemingly inevitable march toward cosmic darkness, the heat death of the universe, a tantalizing question emerges. Could there be a rebirth? After trillions upon trillions of years, after the last stars have winked out, after black holes have evaporated, and after even protons have decayed, might something remarkable occur? A cosmic reset, a new beginning? This question takes us beyond conventional physics into a realm where speculation and mathematics intertwine to offer glimpses of possibilities that challenge our understanding of beginnings and endings. The notion that our universe might not end in eternal darkness, but instead experience a rebirth, has fascinated cosmologists for decades. It offers a profoundly cyclical view of existence, one where endings become beginnings in an endless cosmic dance. But is there any scientific basis for such hopeful speculation, or is it merely wishful thinking in the face of cosmic mortality? One of the most compelling theories suggesting a cosmic rebirth is the Big Bounce hypothesis. Unlike the traditional Big Bang theory, which posits that our universe began from a singularity of infinite density and temperature, the Big Bounce proposes that our universe emerged from the collapse of a previous universe. In this model, when a universe contracts to a certain extremely dense state, quantum gravitational effects create an enormous repulsive force, causing it to bounce back into expansion. Our own expansion would thus be merely one phase in an eternal cycle of expansion and contraction. Physicists Martin Boijeveld and Abe Ashtekar at Pennsylvania State University have developed mathematical models within loop quantum cosmology, an application of loop quantum gravity to the early universe, that suggests such a bounce is possible. Their equations indicate that as the universe contracts, the increasing density would eventually reach a critical threshold where quantum effects dominate, preventing the formation of a true singularity and triggering a new expansion phase. If true, our universe might be just one iteration in an endless series of cosmic cycles. What makes the Big Bounce particularly intriguing is how it resolves certain puzzles of traditional Big Bang cosmology. In conventional models, explaining why the early universe was so remarkably uniform, the horizon problem requires an additional mechanism like inflation, a period of extraordinarily rapid expansion in the universe's first fraction of a second. The Big Bounce potentially explains this uniformity more naturally. The extreme mixing of matter and energy during the contraction phase could homogenize the universe before it bounces back into expansion. However, current observations of our universe present a significant challenge to the Big Bounce theory. The discovery in 1998 that the universe's expansion is accelerating, driven by the mysterious force we call dark energy, suggests that our cosmos is not destined for a contraction phase at all, but rather for endless expansion. For a bounce to occur, this acceleration would somehow need to reverse, allowing gravity to pull the universe back together. Some physicists speculate that dark energy might eventually change its nature, transforming from a repulsive to an attractive force. But there's currently no observational evidence supporting this possibility. An alternative to the Big Bounce is what cosmologists call the Big Rip, followed by a new Big Bang. In this scenario, dark energy becomes increasingly powerful over time, eventually growing strong enough to tear apart galaxies, solar systems, planets, and ultimately atoms themselves. The fabric of space-time would be stretched to its breaking point until a phase transition occurs, similar to how water transitions to steam when heated, fundamentally altering the physics of reality and potentially seeding the conditions for a new universe to emerge from the remnants of the old. Physicist Loris Baum and physicist-philosopher Paul Frampton have proposed that after a big rip, the universe might resettle into a state resembling the very early universe, compact and energetic, providing the initial conditions for a new cycle of cosmic evolution. Unlike the Big Bounce, which requires a reversal of expansion, the Big Rip scenario works with the observed accelerating expansion, taking it to its extreme logical conclusion before proposing a reset. Perhaps the most radical rebirth scenario comes from string theory and its extension into M-theory, which envision our universe as a three-dimensional membrane, existing within a higher dimensional space. In the ekpyrotic universe model, developed by Paul Steinhardt, Neil Turok, and others, our universe undergoes periodic collisions with a parallel brane. Each collision releases enormous energy, effectively causing a new Big Bang. In this view, the history of our universe is marked by repeated cycles of brane collisions, with each collision wiping the slate clean and initiating a new cosmic evolution. The ekpyrotic model elegantly addresses certain problems in conventional cosmology. For instance, it explains the flatness and homogeneity of our universe without requiring inflation. Instead, the long, slow approach of the two branes before collision naturally produces these conditions. Moreover, subtle quantum fluctuations generated just before the branes collide could account for the slight variations in matter density that eventually led to the formation of galaxies and larger cosmic structures. While these cyclic models are mathematically sophisticated and aesthetically appealing, they all face a profound challenge: the second law of thermodynamics. This fundamental principle states that the total entropy, the measure of disorder, in an isolated system never decreases over time. If our universe is cyclical, how does it reset its entropy at each new cycle? Without some mechanism to reset the clock, each successive universe would begin with higher entropy than its predecessor, leading to increasingly disordered and chaotic conditions that would eventually make complex structures like galaxies, stars, and life impossible. Roger Penrose's conformal cyclic cosmology offers a potential solution to this entropy problem. Penrose suggests that when the universe reaches maximum entropy and all matter has decayed into radiation, the distinction between the infinitely large and the infinitesimally small becomes mathematically insignificant. In this state, the universe's end configuration becomes indistinguishable from the low entropy conditions of a new Big Bang, allowing the cycle to restart without violating thermodynamic laws. Penrose's theory makes a remarkable prediction. The collision of supermassive black holes in previous cosmic eons should have left faint, circular patterns in our cosmic microwave background radiation, the afterglow of our own Big Bang. Penrose claims to have identified such patterns, though many cosmologists remain skeptical, noting that similar patterns could arise from random fluctuations. Nevertheless, the theory remains one of the most mathematically rigorous approaches to cosmic cyclicity. Beyond these specific models, lies a more speculative realm of possibilities. Could intelligent life, in its most advanced form, play a role in universal rebirth? Freeman Dyson, Lee Smolin, and other theoretical physicists have contemplated whether sufficiently advanced civilizations might somehow trigger the birth of new universes, effectively becoming cosmic gardeners. While such scenarios may seem like science fiction, they highlight a fascinating potential connection between consciousness and cosmic destiny. For instance, in Smolin's theory of cosmological natural selection, universes that produce many black holes generate more offspring universes, with each black hole potentially creating a new cosmos with slightly different physical properties. If intelligent civilizations could master the technology to create black holes, a possibility far beyond our current capabilities, but perhaps not forever out of reach, they might become active participants in this cosmic evolutionary process. This represents a kind of biological metaphor for universal reproduction, with intelligent life playing the role of reproductive mechanism. More speculative still is the possibility that advanced intelligences might create basement universes, entirely new cosmic domains engineered through a profound mastery of quantum gravity. Physicist Edward Fahey and others have developed theoretical frameworks for how tiny, laboratory-created black holes might inflate to become separate space-time regions with their own physical laws. While the energy requirements for such engineering would be astronomical by our standards, they may not be insurmountable for post-biological civilizations operating over timescales of billions or trillions of years. These speculations raise profound philosophical questions. If intelligent life can create new universes, might our own universe be the creation of a previous cosmos's advanced civilization? This idea, sometimes called cosmological natural selection with intelligence, suggests a kind of cosmic inheritance, where the knowledge and purposes of previous universal civilizations might somehow be encoded in the fundamental constants that make our existence possible. Moving beyond scientific theories into the realm of comparative mythology, we find that the concept of cosmic cycles is far from new to human thought. Ancient Hindu cosmology described vast cycles of creation and destruction called kalpas, each lasting billions of years. The ancient Greeks spoke of ekpyrosis, periodic destructions of the world by cosmic fire, followed by renewal. These mythological frameworks suggest that cyclical thinking about the cosmos runs deep in human intuition, appearing independently across diverse cultures. What's remarkable is how modern cosmological models, built upon mathematics and observational evidence rather than mythology, have in some ways circled back to these ancient intuitions. The sophisticated equations of loop quantum cosmology or conformal cyclic cosmology might be expressing, in the precise language of mathematics, concepts that human imagination has grasped in more poetic forms for millennia. That beginnings and endings are not absolute, but parts of greater cycles. Whether our universe will experience a rebirth remains an open question at the frontier of theoretical physics. The mathematics of quantum gravity, still incomplete, may eventually provide more definitive answers. For now, these theories remind us of the provisional nature of our cosmic understanding and the remarkable fact that the human mind can contemplate such vast possibilities at all. Perhaps the most profound aspect of these cosmic rebirth theories is what they suggest about the nature of time itself. In conventional thinking, time is linear, flowing from past to future in a straight line. But cyclic universe models suggest something more complex. Time as an endless spiral, where patterns repeat but never exactly. This view challenges our most fundamental intuitions about beginnings and endings. The concept of eternal return, that all configurations of matter and energy must eventually repeat in an infinite universe, takes this idea to its logical extreme. If time is truly infinite and matter finite, then eventually all possible arrangements of particles must recur. Philosopher Friedrich Nietzsche was haunted by this concept, seeing in it both terror and affirmation. Modern physics suggests that quantum uncertainty might prevent exact repetition, but the broader question remains: in an eternal cosmos, What meaning do we assign to uniqueness, to the unrepeatable moment? If our universe does experience a rebirth, would any trace of our existence carry over into the next cosmic iteration? Most cyclic models suggest not. Each reset would be complete, with no memory or information transferred between cycles. Yet some speculative frameworks propose that certain fundamental patterns might persist, like echoes reverberating across cosmic epochs. These patterns wouldn't preserve specific information, the positions of galaxies or the history of civilizations, but might encode broader structures, statistical distributions, or even mathematical relationships. The possibility of cosmic memory raises thought-provoking questions about purpose and meaning. If each universe leaves some imprint on its successor, might there be a directionality to cosmic evolution, a trend toward greater complexity, consciousness, or some other quality across cycles? Such questions bring us to the boundary between physics and metaphysics, where measurable quantities give way to values and meanings that science alone cannot resolve. For 21st century humans, these grandiose cosmic cycles might seem irrelevant to daily existence. After all, even if the universe will be reborn, it won't happen for trillions upon trillions of years, long after our species, our planet, and even our galaxy have vanished. Yet there's something deeply meaningful in contemplating these possibilities, in stretching our minds to encompass timescales so vast they defy ordinary comprehension. When we consider cosmic rebirth, we participate in what might be called deep time thinking, the cognitive extension of our awareness beyond human timescales into the almost unimaginable durations of cosmic evolution. This mental exercise doesn't just expand our understanding of physics, it transforms our relationship with time itself, helping us see our present moment as part of something far greater than human history. Perhaps most remarkably, these theories suggest that the physical universe itself might possess a kind of immortality. Even if every star burns out, every black hole evaporates, and every particle decays, the cosmos as a whole might continue through endless cycles of death and rebirth. While individual configurations of matter come and go, including our bodies, our civilization, and our entire biosphere, the underlying reality that gives rise to these phenomena may be eternal. This perspective offers a curious kind of cosmic consolation. While we as individuals are transient, we are part of a universe that might, in some form, endure forever. Our atoms will be recycled countless times in the eons ahead, perhaps eventually becoming part of new stars, new planets, and potentially new forms of consciousness. As the poet Walt Whitman intuited, "I bequeath myself to the dirt to grow from the grass I love. If you want me again, look for me under your boot soles." The cyclical universe concept also challenges us to reconsider what we mean by creation. In traditional cosmology derived from Western religious thought, creation is often viewed as a singular event, a beginning point from which time unfolds linearly. Cyclic models suggest a different paradigm, creation as an ongoing process without absolute beginning or end. In this view, the universe is not so much a made thing as a happening thing, a continuous creative unfolding rather than a finished product. This perspective aligns surprisingly well with certain Eastern philosophical traditions. The Buddhist concept of sunyata, emptiness, suggests that nothing possesses independent, permanent existence. Rather, all phenomena arise through interdependent processes. Similarly, the Taoist notion of Wu Wei describes nature as an endless self-generating process rather than the product of a creator. These ancient wisdom traditions seem to have intuited something that modern physics is now expressing mathematically. That process may be more fundamental than substance. The next Big Bang, if it occurs, would represent not just a physical reset, but a philosophical one. A reminder that endings contain the seeds of beginnings, that destruction and creation are two aspects of a single process. It suggests that the cosmos embodies a profound paradox. It is both ephemeral in its specific configurations and eternal in its underlying patterns and processes. Each universe is unique, yet part of an endless succession. As we contemplate these vast cycles, we might find wisdom in the ancient symbol of the Ouroboros, the serpent eating its own tail, which appears across diverse cultures from ancient Egypt to Norse mythology. This symbol captures the self-referential nature of cosmic cycles, where endings become beginnings in an endless loop. Modern cosmology, with its sophisticated mathematics and precise observations, is in some ways rediscovering this ancient intuition that creation and destruction, beginning and end, may be artificial distinctions in a reality that transcends both. Whether the next Big Bang represents a complete reset with no memory of what came before, or whether it carries forward some imprint of previous cosmic epochs, it reminds us that the story of the universe is far from complete. The cosmos we observe today, with its galaxies, stars, planets, and the brief miracle of conscious life, represents just one chapter in a narrative that may extend far beyond our comprehension. For creatures whose lives span less than a cosmic instant, whose civilization has existed for the merest blink of cosmic time, our ability to conceive of these enormous cycles represents something remarkable. The universe, through us, has developed the capacity to contemplate its own rebirth. We may never witness the next Big Bang, but in imagining it, we participate in a kind of cosmic self-awareness that transcends our biological limitations. As the poet T.S. Eliot wrote, "In my beginning is my end, in my end is my beginning." These words, written about human existence, apply equally well to the cosmos itself. The next Big Bang, should it occur, would be both an ending and a beginning, the final punctuation mark of our universe's story and the opening line of another. In contemplating this possibility, we glimpse something profound about reality, that transience and permanence, uniqueness and repetition are not opposites but complementary aspects of a cosmos deeper and stranger than our linear intuitions can fully grasp. As we conclude our journey through the grandest events of cosmic time, phenomena that will unfold on timescales so vast that humanity, in its current form, will never witness them, we are left with a curious mixture of emotions: wonder at the magnificent sweep of cosmic evolution, humility at our brief moment on this stage, and perhaps a touch of melancholy at all we will never see. This tension between the brevity of human existence and the near eternity of cosmic time creates what might be called the central paradox of cosmology. We can comprehend events we will never experience. The universe operates on timescales that dwarf human existence by factors beyond easy comprehension. While our lives unfold over decades, cosmic processes require millions, billions, or trillions of years to complete. A human lifespan of 100 years represents just 7 billionths of Earth's history, compared to the potential future lifespan of the universe, which might extend to 10 to the power of 100 years or beyond. Our existence is briefer than the blink of an eye. This disparity creates a profound asymmetry in our relationship with the cosmos. We can look back in time, observing light from ancient stars and galaxies that began their journey toward Earth billions of years ago. Through this cosmological window to the past, we've pieced together the universe's biography, from the Big Bang to the formation of galaxies, from the birth of our sun to the emergence of consciousness on at least one small planet. Yet while we can witness the universe's past, we can only imagine its future. The collision of the Milky Way and Andromeda, the death of our sun, the evaporation of black holes, the potential rebirth of the cosmos. These chapters in the cosmic story will unfold long after humanity has likely vanished. This temporal limitation might seem tragic. We are like readers who discover an epic novel, but can only read its opening chapters before the book is taken away. We can infer the plot's direction, make educated guesses about how certain storylines might develop, but we cannot turn the pages to confirm our suspicions. The universe has written a narrative that extends far beyond our ability to witness its conclusion. Yet there is a remarkable beauty in this situation as well. Through mathematics, physics, and astronomy, we've developed the capacity to project our understanding forward in time, modeling cosmic events that will occur billions or trillions of years in the future. Our minds can voyage where our bodies cannot, using the laws of physics as vessels to navigate the deep waters of time. In this way, we transcend our biological limitations, becoming temporal explorers who map the far future through the power of scientific understanding. Consider what an extraordinary achievement this represents. From a species whose ancestors once measured time by the cycles of the moon and seasons, we have developed the ability to calculate the lifespan of stars, predict the merger of galaxies billions of years hence, and model the behavior of black holes as they slowly evaporate across timescales of 10 to the power of 67 years or more. We are creatures of the moment who have learned to think in terms of eternity. This capacity for deep time thinking may be one of humanity's most remarkable cognitive developments. Most animals experience time in the immediate, the next meal, the next season, the next mating opportunity. Even our closest relatives among the great apes show limited capacity for long-term planning. Yet humans have evolved the ability to contemplate events that will occur long after our individual lives, our civilizations, and perhaps even our species has passed into history. This temporal extension of consciousness represents a kind of cognitive transcendence, the mind reaching beyond its biological constraints to touch the almost infinite. The future events we've explored throughout this journey, the Andromeda Milky Way collision, the death of our sun, the fate of black holes, the possible rebirth of the universe, these are not merely scientific predictions. They are achievements of human imagination disciplined by the rigors of physics and mathematics. In projecting our understanding into the far future, we perform an act of intellectual daring that connects our brief moment of awareness with the vast sweep of cosmic time. There is something profound in this connection. Though we are transient beings, through our scientific understanding, we participate in the almost eternal. Though our individual lives are brief, our collective knowledge creates a bridge across the chasms of time. The equations we write today, describing the evolution of stars or the evaporation of black holes, may outlive us by billions of years, carried forward by future civilizations, or perhaps preserved in forms we cannot yet imagine. This perspective offers a curious kind of immortality, not of the body or even of the individual consciousness, but of understanding. The insights of Copernicus, Newton, Einstein, and countless other scientists continue to shape our view of the cosmos centuries after their deaths. Their minds live on in the equations and models that allow us to map the universe's future. In this way, science creates a form of legacy that transcends the brevity of a single human life. Yet, this scientific legacy also illuminates a poignant truth. The universe continues with or without us. The stars will burn, galaxies will collide, black holes will form, and eventually evaporate, regardless of whether human eyes are present to witness these events. The cosmos does not require observers to unfold its immense story. This realization can be both humbling and liberating. We are not necessary to the universe, yet we are privileged to comprehend it during our brief moment of existence. As the poet Robinson Jeffers wrote, "The tides are in our veins, we still mirror the stars. Life is your child, but there is in me, older and harder than life, and more impartial, the eye that watched before there was an ocean." We carry within us the elements forged in ancient stars. Our bodies are literally made of stardust, yet we also carry something more: the capacity to know our cosmic origins and project our understanding into the distant future. We are simultaneously insignificant in the face of cosmic immensity and remarkable in our ability to comprehend it. This dual awareness of our cosmic insignificance and our cognitive significance creates a unique perspective that might be called cosmic humility. We recognize our small place in the universe's vast expanse of space and time, yet we also acknowledge the wonder of a consciousness that can grasp the principles governing this immensity. We are tiny but aware, brief but understanding. Cosmic humility doesn't diminish humanity's value. Rather, it contextualizes it. Against the backdrop of stars that live for billions of years and processes that unfold over trillions, the brevity of human existence might seem to render it insignificant. Yet perhaps the opposite is true. Perhaps it is precisely our transience that makes consciousness so precious. Like a rare astronomical event, visible for just moments, the flash of aware life in the cosmos may derive its value partly from its scarcity across cosmic time. The universe we've explored throughout this journey, from colliding galaxies to dying stars, from evaporating black holes to potential cosmic rebirths, is one governed by consistent physical laws. These laws allow us to project current understanding into predictions about events billions or trillions of years hence. Yet this consistency also highlights one of the great mysteries of existence. Why is the universe comprehensible at all? Why should the human mind, evolved on one small planet primarily to ensure survival and reproduction, be capable of grasping the mathematics that describes black hole thermodynamics or the potential for cosmic rebirth? Physicist Eugene Wigner called this the unreasonable effectiveness of mathematics in describing the natural world. There seems to be a profound harmony between the structures of human thought and the structures of physical reality, a correspondence that allows us to model events across vast gulfs of time and space. This correspondence is not something we should take for granted. It represents another facet of the unique relationship between conscious observers and the cosmos they inhabit. As we contemplate the far future events that humanity will never witness directly, we might find solace in the knowledge that our scientific understanding itself represents a kind of witnessing. Through the disciplined application of observation, mathematics, and theoretical physics, we've constructed a window into the deep future, not as clear or certain as our observations of the present, perhaps, but nonetheless a genuine form of seeing across time. We observe the future universe not with telescopes, but with equations and models that extend the arc of known physical processes into the distant future. This scientific foresight connects us to something beyond ourselves, to timescales that dwarf human existence and phenomena that transcend human experience. In this connection lies a curious kind of meaning. Though we will never see the Andromeda Galaxy merge with our Milky Way, though we will never witness the final evaporation of a black hole or the potential rebirth of the cosmos, our ability to anticipate these events links us to the grand narrative of cosmic evolution. There is something almost spiritual in this connection across time, a thread that binds our brief moment of awareness to the almost eternal processes of cosmic evolution. Though we occupy an infinitesimal slice of the universe's timeline, through our understanding, we participate in something approaching the infinite. Our consciousness touches events separated from us by billions or trillions of years, creating a mental bridge across the chasms of deep time. This perspective might offer some consolation for our cosmic impermanence. While individual humans live for mere decades, and even our species may exist for only a few million years, a blink in cosmic time, the understanding we've developed, the insights into stellar evolution, galactic dynamics, black hole thermodynamics, and potential cosmic cycles, connects us to processes that span almost eternity. In comprehending these distant future events, we transcend, at least intellectually, the limitations of our brief existence. As we conclude this exploration of the universe's grandest events, phenomena we'll never witness directly, perhaps the most profound realization is how fortunate we are to exist during the universe's vibrant youth. We live in what cosmologists call the stelliferous era, the period when stars illuminate the cosmos and complex structures readily form. This era represents just a fraction of the universe's potential lifespan, yet it's the period most conducive to life and consciousness as we understand them. We exist at a time when the night sky blazes with billions of visible stars, when galaxies cluster close enough to study, when the cosmic microwave background radiation still carries the imprint of the Big Bang, when the universe remains dynamic and energetic. In cosmic terms, we inhabit a remarkable epoch, not too close to the Big Bang when matter was too hot and chaotic for complex structures, nor too far into the future when stars have burned out and galaxies have drifted beyond visibility. Our moment in cosmic history is privileged. occurring when the universe is neither too young nor too old to support complexity. This timing isn't coincidental. Life requires stars to forge heavy elements and provide energy, planets to offer stable environments, and sufficient time for evolutionary processes to produce complexity. We exist when we do precisely because this era of cosmic history supports our existence. Nevertheless, recognizing this privileged moment in time should inspire both gratitude and responsibility. Gratitude for existing during the universe's most vibrant chapter, and responsibility to appreciate and understand the cosmic context that makes our existence possible. As inheritors of the universe's complexity, we bear a unique responsibility to witness, to understand, to preserve knowledge that might otherwise be lost. In a cosmos where entropy increases and information tends to be scattered and lost over time, consciousness creates local pockets where information is gathered, structured, and preserved. Our scientific understanding represents such a pocket, a repository of knowledge about cosmic processes that might, in principle, be carried forward into the future. Whether human knowledge will survive for thousands, millions, or billions of years remains uncertain. Our species may evolve into forms we wouldn't recognize, transfer its consciousness to non-biological substrates, or perhaps eventually go extinct like countless species before us. Yet the understanding we've developed, the mathematical descriptions of cosmic processes, the predictive models of events billions of years hence, represents a potential legacy that transcends our biological limitations. In developing this understanding, we've achieved something remarkable. We've extended our awareness beyond the constraints of our biological existence. Though we will never witness the collision of the Milky Way and Andromeda galaxies 4 billion years from now, though we will never see the Sun expand into a red giant in 5 billion years, though we will never observe black holes evaporating over trillions upon trillions of years, our mathematical models allow us to project these events with reasonable confidence. In this way, science offers a form of time travel, not of the body, but of the mind. This mental time travel represents one of humanity's most profound achievements. We are creatures who evolved to track immediate threats and opportunities, predators, prey, mates, seasonal changes, yet we've developed the capacity to model events billions or trillions of years in the future. This temporal extension of awareness represents a kind of cognitive transcendence, the mind reaching beyond its biological constraints to touch the almost infinite expanse of cosmic time. As we contemplate the universe's grandest events, phenomena beyond direct human experience, we might find both sobriety and wonder in this perspective. Sobriety in recognizing our temporal insignificance against the backdrop of cosmic evolution, and wonder in appreciating our cognitive significance as beings who can comprehend this evolution. We are simultaneously humbled by the immensity of cosmic time and elevated by our capacity to understand it. Perhaps this dual awareness of our cosmic insignificance and our cognitive significance offers wisdom for navigating our brief moment in the universe's story. We might learn to value our transient existence precisely because it is transient, to appreciate consciousness more deeply because we recognize its scarcity across cosmic time, to preserve and extend our understanding as a legacy that might outlast our biological existence. In closing this journey through cosmic time, from colliding galaxies to dying stars, from evaporating black holes to potential cosmic rebirths, we return to a simple yet profound recognition. Though we will never witness the universe's grandest events, in contemplating them, we participate in something approaching the eternal. Our consciousness, though brief, touches processes that span billions or trillions of years. Our understanding, though incomplete, connects our momentary existence to the almost infinite unfolding of cosmic evolution. This recognition doesn't erase the poignancy of our cosmic impermanence, but it does transform it. We are not merely transient beings in an eternal cosmos. We are transient beings who comprehend this eternality. In that comprehension lies a kind of transcendence, not of our physical limitations perhaps, but of our temporal ones. Through science, we project our understanding forward in time, modeling events we will never experience directly, but nonetheless grasp intellectually. As the astronomer Carl Sagan observed, we are a way for the cosmos to know itself. In developing the capacity to understand events billions or trillions of years in the future, humanity has achieved something remarkable. We've become a means by which the universe contemplates its own destiny. Though we occupy the briefest moment in cosmic history, through our understanding, we participate in the almost eternal story of cosmic evolution. The universe's grandest events will unfold long after humanity has likely vanished. Yet in another sense, we've already witnessed them, not with our eyes, but with our equations, our models, our disciplined scientific imagination. In this intellectual witnessing lies a profound connection between the fleeting and the eternal, between our momentary awareness and the almost infinite expanse of cosmic time. We are brief, but our understanding touches the eternal. As we close this exploration of cosmic futures, perhaps we might find inspiration in the words of the poet Walt Whitman. I bequeath myself to the dirt to grow from the grass I love. If you want me again, look for me under your boot soles. Our bodies will indeed return to the cosmos from which they came, our atoms dispersing to become parts of future stars, planets, and perhaps even living beings. Yet our understanding, the mathematical and physical insights that allow us to project cosmic evolution forward in time, represents another kind of legacy, one that might survive in forms we cannot yet imagine. In contemplating the universe's grandest events, phenomena beyond direct human experience, we've engaged in an act of intellectual daring that connects our brief moment of awareness with the vast sweep of cosmic time. Though we will never witness these events directly, through our understanding, we've already, in a sense, seen them, and in that seeing lies a kind of immortality, not of the body or even of the individual consciousness, but of comprehension itself. The universe continues, with or without us. Stars will burn out, galaxies will collide, black holes will form and eventually evaporate. The cosmos may experience rebirth, all according to physical laws we've begun to understand. In developing this understanding, humanity has achieved something remarkable. We've transcended, intellectually, if not physically, the temporal constraints of our existence. We've become a way for the cosmos not just to know its present, but to anticipate its future. As inheritors of this understanding, we bear both a privilege and a responsibility. The privilege of comprehending cosmic processes that span almost eternity, and the responsibility of preserving and extending this comprehension as a legacy that might outlast our brief moment in the universe's story. In this legacy lies a connection between the fleeting and the eternal, between our momentary awareness and the almost infinite expanse of cosmic time. Though we will never witness the universe's grandest events, in comprehending them, we participate in their unfolding. We are, in a profound sense, already there, present not physically but intellectually at the collision of galaxies billions of years hence, the death of stars, the evaporation of black holes, the potential rebirth of the cosmos. Through our understanding, we've extended our consciousness beyond the constraints of our biological existence to touch the almost eternal processes of cosmic evolution. In this extension lies both the beauty and the tragedy of human existence. The beauty of a consciousness that can comprehend events separated from us by billions or trillions of years, and the tragedy of a lifespan too brief to witness these events directly. Yet perhaps this very tension between comprehension and experience, between understanding and witnessing, creates the unique perspective that makes human consciousness so remarkable. We know more than we can experience, understand more than we can witness, comprehend more than we can directly observe. As we conclude this journey through cosmic time, we might find both humility and wonder in this recognition. Humility in acknowledging our cosmic impermanence, and wonder in appreciating our capacity to transcend through understanding the temporal constraints of our existence. We are brief, but our comprehension touches the eternal. We are transient, But our understanding participates in the almost infinite unfolding of cosmic evolution. The universe's grandest events will occur long after we're gone, yet through science, we've already, in a sense, seen them. And in that seeing lies a profound connection between our momentary awareness and the vast sweep of cosmic time. A thread that binds our brief existence to the almost eternal processes that shape the cosmos. Though we occupy the merest instant in the universe's story, through our understanding, we participate in the whole of it. The universe continues, with or without us. Yet while we're here, we comprehend it. And in that comprehension lies something approaching the eternal.